Plan B machen kann. Können die mir vorstellen? Na gut, aber wenn das extra installieren muss, dann nicht. Ja. Okay, welcome everyone to this workshop on experiences in short-term prediction and gaps in research that we're organizing from the IEA WIND Task 36 on forecasting. The task has been started in January with a kickoff at RISU, and one of the things that we decided on that was to have a public workshop trying to get to the bottom of what are the issues that we really need to address for the 3-year period of that task, and possibly for the second round of the task as well. Also, what are the issues that we should try to get into the different research agenda, for example, of the European Union, or also national providers? And what are the tasks that are worthwhile investigating, and what are tasks that are maybe not so important? That's the basic idea of this workshop, and I'm happy to say we've got some close to 40 people that are going to be here, plus another 40 people that are connecting via the web, and I hope that is actually working. I have no feedback so far, but I'll try to get the questions from the web stream in via monitoring the Gmail, the corresponding Gmail account and chat function of the stream. That includes people that currently are in Washington State, and I've got an email from this morning already. So that's I will. Having said that, I would like to take the opportunity to thank our host, Pep Moreno, and his company Vortex for graciously hosting this event. And Pep is going to come up and say a few words about the logistics and maybe Barcelona as such.
Okay. Good morning and welcome to our hometown. It will be much hotter later, so enjoy the fresh right now, because it is what we can offer you. We are in this complex. This venue where you are located now is part of a facility of the hometown of Barcelona hometown for the mature startups that grow and may leave this place in a longer time. We are located upstairs in some offices here, and this is kind of a nest for the entrepreneurs, for the companies to be protected from the outside world that is very wild. And this is in fact. My colleague Hill will talk amply about this, because we as a modelers we don't sometimes we are not so aware that how tough are the final users. Okay, the final users' perception of what is modeling performance is quite different of what us as modelers think. We are very happy of things, and they are very angry at the same things. Okay. Regarding the logistics, we will stay here until 11. At 11, it will be a coffee break just here outside. This will last half an hour, maybe, or so. Then we come back to the talks, and around 1, we will go to the cantina, which is just few steps away at the end of the corridor. And then there in the terrace, there is a small lake. There will be a stand-up with enough shadow for for the sun. Okay, so we will have this lunch. Come back here, and at let's say 3:30 or so, it will be another coffee break, and this until the end of the session, which, if I remember well, it will be about 5 or 5:30. Okay, and then we didn't arrange anything for the for dinner, because this is a very touristic city, and I guess you would like to explore it by yourself. It's plenty of things. But if you are a bit lost or you want some advice, just ask us, and we can tell you some restaurants or so, or even organize things. So since we are not so many, we didn't organize a formal dinner, but it's full of opportunities. Tomorrow, this will be again coffee break at 11, and lunch, stand-up lunch there outside at 1. Normally people here eat much later, so we will be there quiet and even fresher than the normal lunchtime here. And that's all for my... Thank you for coming.
Thank you very much, Pep. And with that, we should go directly to the first talk of the day, which is the keynote speak by Helmut Frank from Deutscher Wetterdienst. He is one of the investigators in, amongst others, the Eveline project, but also generally involved in improvements of the numerical weather prediction model at Deutscher Wetterdienst. And he is, amongst other things, also the work package lead of the numerical weather prediction work package, which means that he took it upon him to try to assess in a bit wider sense who is actually doing which kind of improvements in the international arena. And he contacted quite a number of people to get the answers for that. Please.
Thank you, Gregor. Good morning, everybody. I contacted several people, but now I have to open the correct one. Yeah, this one. Really, direct replies I got from... First, I have to thank Clive Wilson from the Met Office. He contributed, direct some slides, and also Malte Müller from MetNo, and had a loose contact with you, but direct replies I got from them, and I try to give a more general overview of numerical weather prediction, how it's done, how it has improved over the years. I just received the last slides maybe less than half an hour ago, so it's not so perfect. There were some complications in the communication, but let's still try to. So let's say some state of the art, and then with as I said, Malte Müller, Clive Wilson, then also lots of slides, advice from other colleagues from DWD, and also what I found in literature. And I want to start first with a slide of the problems. The problem, in a way, you could say, is the weather forecasting problem. That's in the Eveline project at DWD. Colleagues investigated what are the, where do the biggest errors come from, and then they took 100 days with the largest day ahead power forecast errors, and looked how it relates to the weather, how it correlates to the weather. In a way, you can say, and so the most critical is the frontal passage, the position and timing. And so that's what I mean. You could say that's the big weather, when the general weather, which naturally influences then the surface wind or the wind in the boundary layer, and then the wind power forecast. Other problems, especially related to winds, are then stratification, especially stable stratification, which is in winter a problem. when the wind profile is not good, and where the opposite then in the summer, then the daily cycle of the wind speed, which is still a problem. There, I would say, one thing is that even 10 years ago, I think, would say, weather services didn't look so much, or didn't look much at the wind in 100 meters. I mean, there was no client for it there. There's the surface wind, the 10-meter wind, that's the standard quantity for in weather forecasting. And naturally, then there is the wind at the higher levels for the aviation, but at 100 meters there wasn't much. Now the power plants, wind power plants, they are around 100 meters to 200 meters. So that's really now where a lot of interest is going in, where it's very important, but there is not so much data also. So, where are we? Let's just say a bit about the trends, how it's going. Trends of the models going to higher resolution. Then I want to say a bit about physics. Actually, then ensembles. And then want to point out new data, which promises then to improve also then the forecast. For power forecasting, the focus still is, as far as I see it, I'm not an expert in power forecasting, but still is the day ahead, also, as far as I know. So that's the short range for weather forecasting. Here, that's the slide illustrating the improvements over the many years in weather forecasting. That's from the Met Office, but I don't know actually which model now, the global, I guess. And that's the surface pressure. So that you can say then relates to weather patterns, so the fronts, for example. And so it's improving, but progress is more or less constant, but it's slow, you could say. You get 1 day improvement over a decade. So that's how it is. In a way, it is also naturally the models are better and better, so it's more difficult to improve them. Here another one, the slide. One was the surface pressure. This is now wind. I couldn't find a verification of wind at, let's say, 100 meters or 200 meters, a long time series, because as far as I know, it doesn't exist. That's why I wanted to have something with wind, so I took wind at 925 hectopascal. So it's in the boundary layer, but a few hundred meters above sea level. And that's from our global models at DWD. Same measures, it's improving. Let's go back. There's a big change. This is when we introduced our new model, the ICON at DWD. So that's, but otherwise, it's slowly improving, and I don't expect another big change like this in the next 3-4 years at or 5 years at DWD. So, where are we going? It's going to a higher resolution. So this is from the Met Office, a comparison of now that's the surface wind, 10-meter wind. Can you see? 10 meter, that's actually too low now for wind power. I think there's no power plant that is doing anything with 10-meter wind, but that's what you have in meteorology still, where we have data. And then you see when you go to higher resolution, then you get better forecasts. But there, main improvement also that you resolve the orography better, and then when you come close to the orography, naturally it helps if you have a better resolution. More details. Then I want to show you just an illustration what kind of data is used by weather forecast, numerical weather prediction models. I take data from which was used by our global model ICON for the data assimilation at the 19th of May this year, 0 UTC. And I don't even show all, but first you start with the synop data, so that's the surface data, and there the most important one is the surface pressure. Then we don't use temperature. 10-meter wind is only used at, not used much because it's so much influenced by local conditions. It's difficult to assimilate. This is done, synop data is at the over land mostly of some islands. And here the next one are buoys over, to get some information over water. And that's also surface data, but that's surface wind from scatterometers. So that's satellite data, but at the surface. Now let's move a bit higher. That's our temp radio sound data. And there you see the problem with the, let's say, conventional data. It's mostly over land and mostly in the northern hemisphere. So when you're looking into the southern hemisphere, there's not much there, hardly anything. Yeah, lots of data you also get from aircrafts, which is a big source. But here's a similar problem to the radio sounds. It's mostly in the northern hemisphere. There is a lot of air traffic. There over the Indian Ocean and the southern oceans, there's almost nothing. So that's big holes there. This is, now we're coming, the rest is the satellite data. This is our AM atmospheric motion vector winds. This is from global geostationary, most of it from global geostationary satellites. There you have a global coverage, that's very nice. Now that's microwave data from AMSU instruments. There that's the big advantage. You can have lots of data and you have global coverage, real global coverage, which makes, that's infrared data. And another nice instrument is here the radio occultations from the global GNS, global navigation satellites, and where you get information of the humidity. And what's so nice about it is this is really a global distribution quite evenly, so that's very good. Then there's additional data here from another satellite, and then wind profiler data I didn't show, but it's just an illustration, and that's from the global model. There are, I'll show later some other ones, just to show you what's going into the data assimilation to get the initial state for a weather forecast model. And now an illustration more on the resolution, how it's improving. This is from, I got from the Meteorological Institute in Norway. This is their model, AROM, in cooperation with Meteo France also. And they run it together with the Swedish Weather Service. That's the Met Co-op. So that's, they have run one model for Norway and Sweden. And the resolution is 2.5 kilometers. And that's what is, the next illustrates here what you get from this. So this actually you get lots of details. And yeah, that's what you can get from today from weather forecast models. It's just an illustration of a list of a few models. Doesn't claim to be, no, there are many missing. I just wanted to include participants here of the IEA, or some of you. You see that the global models on the left, they have now resolutions below 20 kilometers, and with the limited area models, we're down to the kilometer scale. Meteo Swiss, Swiss Weather Service, they have now also a Cosmo version running at 1.1 kilometer every day. And so that's, the trend is going to a higher resolution. This is, then you get more realistic weather forecasts. You can simulate, actually already start simulating convection. The problem, you have lots of details in the orography and the land use. But the problem is the weather isn't deterministic, so it easily can happen that actually you get, it looks very good, the weather, it's the right weather, but maybe the localization is not perfect. And then you have the double penalty, so that you have get the right weather at the wrong place. In the wrong place I mean just a few kilometers. But because your resolution is just a few kilometers, you're off. And then you get an error. Now it's a bit mixed up now. This is another illustration from the UK, which where they started to run for the Olympics in London there, for the sailing there, a version of the model at 330 meters. So here's the orography at 333 meters. On the right, it's the UKV, the 1.5 kilometers. 1.5 is already very good, but naturally with 330 you resolve here this peninsula very well. And this is an illustration here. Then just now you can see that's the 10-meter wind, and you can even see the details of the cloud streets there, and then how it influences the wind. And here this peninsula where I think the sailing competitions there were in this bay. The problem is that the more also when you resolve smaller details, they have you cannot predict them long in advance, so the predictive range is very shorter than for larger scales. So that's I don't know how long is the model run, Clive? For how many hours? 18 hours. 18 hours. So an 18-hour forecast is made. No day ahead forecast. And he told me that a version of this model is now running for London each day. It's not really operational, but still it's done every day, and forecasters also look at it. But here an illustration what on the rough scale now, with this, what I said, the double penalty, this is just the verification of wind at 1,000 hectopascals, or surface wind, you can say, from our global model. If you do it on a 0.25 degree grid, or aggregate everything to 1.5 degree. WMO verification and comparison of models is done at 1.5 degree. So that's 100, say a scale of 100 kilometers. And you see, if you have larger fields, larger scale, smoother fields, then you get better scores. So that's the problem when you do fine resolution. Depending which score you look at, it might look worse than the rough resolution. Now I want to come a bit more to model physics, what's been done, and there I found what I think is a good illustration of work by Sandhu published in 2013 with the IFS from ECMWF. The problem was and still is in some respect that the weather forecast model, especially also then global models, often the diffusivity is they need some, to stabilize the model, they need some minimum diffusion, and often the diffusion is too high, so which makes had then a negative impact on the wind profile, which is shown here on the left. This is at the Cabau Tower, January 2011, and that's how the average profile looks like there. And what when they did there, it was this work. This was from the model. The average wind profile, the control here looked like this. So it wasn't, the wind was too weak. This was because the diffusion was too strong. It was too, as you can say, the friction was too strong. No, this was not. So then they made a few changes to change a little bit the long tails of the stability functions. Also then reduce the other one, the LT30 is reduction of the limiting scale of the Blackadder length scale in the diffusion, which you can see improves the wind profile. But on the right, it should illustrate that actually it had a negative impact on the large scale weather. You can say this is the RMSE of the geopotential at 500 hectopascal, the mid of the atmosphere. That's the standard verification score of use for large scale and global weather forecast models. So that's so they couldn't just introduce it like this. They simply change. So the sentence at bottom, the boundary layer wind improved, but forecast anomaly correlation and RMSE of 500 hectopascal geopotential became worse. In the end, they still could introduce changes then in the global model in November 2013, but it had to be done in combination with other changes to the surface track and also to the heat exchange between the land surface and the atmosphere. This is just an illustration how difficult it is to improve forecast models, and it can possibly, if you make an improvement at one place, it can for one variable, it can have a negative impact on other ones, and that's what I want to show. That's the problem. Another illustration is now that's from DWD. This is about the daily cycle in the wind, and it's shown here are the average daily cycle in June 2015 at the mast in Falkenberg in Germany, 100 meters. The top height, the red one, is the 898 meters level, so 100 meters above the surface. Also, what you can see here nicely that how the wind, the daily cycle changes direction with height. At 10 meters, you have the highest wind during the days. The momentum is moved down, whereas during the night here you have the highest wind. At 100 meters you have the highest wind speeds during the night because of low-level jets. And the models have difficulties of representing this. These are our icon, the global model, the Europe nest inside it, and then comes the Cosmo EU model, limited area model, and the Cosmo DE, the high resolution model. And you see that the icon has now the best, represent the daily cycles best, and because they have very similar turbulence models inside them, but icon has an additional dependence on the Richardson number, and this is now also, it will be included, or we are about to include it also in the Cosmo DE. And this is also another illustration that about relations, when you improve models, what you have to do. I remember at the kickoff meeting at Riseux, there was also said that maybe then the weather services could increase the resolution, the vertical resolution, to improve the models, to improve the winds in the boundary layer. But this is an illustration that's not the only thing which helps, because actually this is just on the right you see now wind profiles modeled by Icon and Cosmo, and actually the vertical resolution Icon is worse, it's not as fine as for the Cosmo, and still in this case the daily cycle is better with the Icon. So it's a combination of physics and resolution which makes the improvement. So when another point which you, naturally I talked about how difficult it is to predict the weather, especially when you go to higher resolution. You might have better patterns, but still it's not deterministic, so naturally everybody is going to ensemble prediction. The slide is just an illustration for it's the forecast of wind for the Fino wind mast in the North Sea in Germany, now from our global model. I took it because I think it's a nice slide. But for ensembles, you need ensemble. There are different ways of ensemble generation, perturbations, and then if you have a limited area model, a high resolution model, so kilometer scale, then you also need boundaries, and that's also naturally determines how the ensemble is done. I'm always wondering how important the ensemble forecasts are for the wind power or the service providers, because as far as I know, everybody or most still use data from different weather services, from different models, and usually when you use different models, you even have a better ensemble than using just an ensemble from one model. But actually, I forgot here one point. This one I want to illustrate also from which you use ensembles. There's no perfect ensemble, so to improve the ensemble, it needs a lot of post-processing, and so that's this is just an illustration. That's the rank histogram of the 100-meter wind from the Cosmo DE ensemble, and the problem is most ensembles that often the spread of the model is not wide enough. So often the forecast happens too often that the forecast lies outside of the ensemble range of the forecast. And that's when you have to try to statistically do post-processing to improve this, and then you can get a better, on the right here, a calibrated forecast, where then you better represent the variance which occurs in nature. So with the ensembles, there's a lot of post-processing done, usually calibration MOS, but often, as I said, I think that's also often done also by the service, by the clients who take the weather forecast. Therefore, I think for the weather services, or also for deterministic models now, it's actually even more important that you have an ensemble in the data assimilation, because then you get information on the flow-dependent errors of your model. Classically, you have if you have deviation from the observation to the first guess, then you have to put this into to modify your first guess. And if you don't know anything, only have some climatology, then it's more or less isentropic distribution of the increments, what you do. If you know something about the flow, for example, from an ensemble first guess, then you have some information how you do the increments, how you modify your first guess. And that's an illustration for this. In this case, there's a front here on the east coast of the US, and then you know that across the front, naturally, there is less correlation than along the front. So this is a big advantage if there are gradients, stronger gradients occurring in the weather, and also for a higher resolution, for convective scales, which is very local. If you have some additional information from the ensemble, then this can help a lot to improve your analysis and then also your forecast. And with this, I want to go over to quite a few new, as far as I know, new observation systems, which I think is interesting here, because then if you have newer observations, additional information, then you get a better analysis, and then you get a better forecast, especially a better short-range forecast. And as I said, wind power forecasting, for the most case, this is considered in weather forecasting, this is the short range. Here's just an illustration. I said we use radio occultation data from the global navigation satellite, better known as the GPS satellites, but there are other ones. And here is where you can get additional information from slant total delay between the satellite and the ground station. And this only should illustrate how there are lots of satellites and different ground stations. So actually you can get a lot of additional data which until now is not used. So this is promising data to have additional information on the state of the atmosphere. Another program pointed out by Clive was here is the cost action TOPROF, which has the aim of providing additional boundary, especially also boundary layer information from ceilometers. So there should be over several hundred ceilometers in Europe, which will provide additional information on aerosol and clouds with high resolution in vertical resolution and also in time. More Doppler lidar should be provided, and also additional microwave profilers. Other information is, I said when I showed what data is used, there was this was for our global model. There was no radar data there, but actually for the limited area models, we use some radar data, and others I know also use. But at least right now at DWD, we only use latent heat matching, so only horizontal information on rain or not. But there is much more information in radar data. The reflectivity, the 3D, you have the radar is really looking in the atmosphere, three-dimensional picture you get. Also, you get a picture of the 3D wind, but and that will also be included in the models to get more information. This is just from a first study from a colleague at DWD, showing when she assimilated one radar and then looked how it looks like at the other ones, how it improves. The blue is when you don't have the radar included, and you see it's the worst, it's the highest RMSE. If you assimilate the data, then it's getting reduced. There are different ways of reducing the data amount. That's what you have to do, this super opping. And what you can see here, that until you finally use the data, you have to do a lot of tests. The first thing actually, which is not shown here, is the quality control of the data. And that's essential. I mean, if you know something, how good is the data? How can you trust it? And then you see, how do you include it? How much do you take? These high resolution data, you have to thin it. You cannot include all of it. And another problem is with this data is you might assimilate it. You have it in your initial state, and the problem is that it's not lost in the forecast after only 1 or 2 hours. So that still the information really adapts to the model. It's kept in by the model so that it really improves the forecast. So there's a lot of tuning has to be done until you really can use it, until really it improves the forecast. So that's a slow process which takes quite some time. That's what I want to point out here. This is just one slide from Maintenant, where they have a project to develop an integrated nowcasting approach from coupling a numerical weather prediction model with a wind farm simulators and includes the Meteorological Institute and then also Vestas wind power providers, power plants. Said I don't know the details, but that's also where an illustration where the weather services are cooperating and want to make improved forecast. Now I come to even including more directly wind power. Here I show a slide from the colleague Stefan de Cler from Eveline project in DWD. He made the idea was that with this wind turbines, they are in a way like really big anemometers. So you have a wind measurement at 100 meters, even higher, at a big volume, and it's getting now to the scale of the resolution of the models. Think of the 330 meter resolution of the UK Met Office, what they're doing their research project there. This is, if you have now a big turbine, this is already a big turbine. This fills out horizontally almost half of such a grid cell, and vertically, naturally, it's several grid cells. So you have a real big measurements. It's fascinating to think how can you include this directly in the model and get this data in. And he made a study where he simulated assimilating such data, and then you also get some improvement. That's the red curve here, the two red curves, and the arrow symbolizes how the forecast error then decreases. On the other hand, you also see the problem that you keep how difficult it is to keep this improvement in time. But actually, at least currently, we cannot follow this further. The big problem is, at least in Germany, to get the power data. You don't get up-to-date current data, only historical data, and also the quality of the data is poor, is bad. Just you have to say bad. Just already the metadata with it is often not well documented. So, and the problem then is you have to throw out so much data that there's not much left to assimilate. So that's a real problem. We're also doing studying with assimilating solar power, and this looks more promising. One main reason is there's so much more data included. So after quality control, even if you have to throw out a lot of data, there's still enough left that you can hope for that you get something into the model. Now the second last slide, I want to point out another problem, which as far as I know has not been done by any weather service yet. There has been studies, and that's the question, when do we have to include the wind farms in the numerical weather prediction models because they influence the weather? So this is a map which you see where I got it from the net, which shows current and planned wind farms in the North Sea. And if you look at the size of these areas, they are getting as big as here, the Danish islands there on the right. So this, so you have there suddenly, instead of just water there, which is a relatively smooth surface, you have these wind farms there, which take out a lot of momentum from the wind and create additional turbulence. So the question is, when will they affect the weather, the cyclones, so that you really have to account for them? Not with the idea of having to predict the power there, but just to know what's their influence or how they influence, as I said, the flow over the sea, especially over the sea, naturally also over land, but over the sea the contrast is even bigger. So I don't know of any weather service who really did this, but I think it will come in some years that we'll have to account for it. So that's now the summary. I want to say the numerical weather prediction, it's improving, constantly improving, but it's a slow process. It's going to higher resolution, kilometer scale is done operationally. But you have the problem then with the location, small errors and location errors, then already you see them directly. So that's one way also to overcome then the problem with the non-deterministic weather is then to use ensemble prediction. You can improve the wind forecast, the boundary layer wind forecast with better physics. It's done, yeah, and so that's hopefully also where this IEA task might contribute when they're also providing additional mass data or pointing out additional data. And additional data is assimilated in the weather forecast models, which will improve the initial conditions and then also the forecast. But the problem is quality control, and as I said, I forgot to write here, to keep the additional information in the forecast, so it doesn't, you lose it just after 4 or 5 hours. One point which I didn't have a slide now is the seamless prediction, so that you try to get more or less to have one system, including more going from nowcasting smoothly over to the short range and the medium range, also essentially then to seasonal climate prediction. So that's something which is being done more and more by the weather service. And now the things I don't know, but I am sure they will come, is a simulation of power data or data from the wind power plants, also from solar power, and just accounting for wind farms in the models, not to predict their power, but just to see their influence on the weather. Small issues are things which will be could be done easily. I think maybe there will be no new variables which are of interest to clients. As I said, 100-meter winds is not a standard output quantity by weather models now, but it can be done. Often it's done also more. I don't know if there's interest in higher temporal resolution. Yeah, that's small things which probably will come. Yeah. Thank you for your attention.
Thank you very much, Helmut. I'm sure we got some questions to this. Pep is standing by with a microphone so that the outside people sitting in the stream, I think we're currently having 10 people watching, can also hear it. Let's go first.
I have a question. You mentioned that the wind farms and the offshore wind farms will influence the weather or the weather model prediction quality. Is this maybe not already the case in north of Germany, where we have also a lot of wind farms available and taking out a lot of energy of the weather system?
Yeah,
made any,
as far as nobody really investigated on a real weather models. I know there have been some studies doing artificial putting in something in just a test case or so, but yeah, I don't know. I don't know of any weather service who really put it into their model and made a forecast and see how is the change on the weather. So it has some impact. Maybe, as I said, currently maybe it's not so big still that you really has an impact which you can directly see in the quality of the forecast. But said once you have these big farms there, especially over water, I'm pretty sure we have to they will influence the weather, and then we'll have to include them. Includes some effect. It hasn't to be perfect, but probably it has to be included somewhere.
Maybe I can come with a comment here. In WRF, there are at least two parameterizations for wind farms. One from Fitch, and that's the one that is actually distributed. And we developed one ourselves, the explicit wake parameterization, EWP, from Patrick Volker. So there are, in the research world, there are things underway to actually take them into account, but it's hard to say when they actually arrive at operational weather services.
Then, as I said, we have to make then operational forecasts and to compare with where it's not included. If you really see a difference on the weather models on a daily scale, not only just for a few cases, but for normal operations, and that's not been done as far as I know.
Two questions, please. George Carniotis from Minparitech. The first one, at slide somewhere in the middle, you mentioned that lower resolution models have better scores.
Depending on what score you look at, on how you calculate the score.
Just my question is...
you have smoother fields. So, for example, if you calculate an RMSE, random mid-square error, you have more variance in a higher resolution. So it looks better. It looks worse because of the higher variance. If you just look at compare RMSE, random mean-square error, compared to a low resolution.
Just to be sure, the scores are calculated based on data from measurements from weather stations.
There are lots of different scores. So that's.
No, but I mean, when we use the real data from the weather stations, what is the result?
No, I mean, it could be, depending what you do, it could be that the smoother field or lower resolution, which has a smoother field, yields better results for one score. It depends on the score. I mean, there are lots of anomaly correlation, RMSE, then mean errors, then additional one.
Okay.
So and then you can compare with the analysis of the model. You can compare with the observations. You can compare with lots of observations. You can. So there's lots of scores and. Yeah.
So you present a kind of concluding statement, but I can understand it's very conditional to
yeah, that's what I want to point out. So it's not, you cannot say higher resolution is better. It depends. You have to define actually how you measure what is better, and then it could actually be, depending how you measure, you could say that actually it could look worse.
Okay. Another question. We discuss a lot about integrating in the data simulation process data from the wind farms. What's your opinion? Is it going to improve the performance of the forecasting models? Or?
That was the second last, which I said with the study by Stefan de Cler. It looks like it would improve forecast, but at least our experience in Germany is that the data we got was it was very difficult to get some data, especially not data only. It was only historical data we got, and then the quality was really bad. I mean, for example, it starts already with the timestamp, time information. Could be it was in Central European time. It could be that it shifted when there was a change from daylight saving time to regular time or back, that they didn't make it in time, so it was for weeks it was running on the wrong time. And just such bad quality, how can you use this data in a data assimilation, operational data assimilation, where you do it, the assimilation maybe 1 or 2 hours after the actual time. So you need good data, and you need it in time.
Okay.
And at least from what we had, this was so bad that there was almost nothing left.
In principle, today the weather models use the data from the 2000 stations, if I'm not mistaken, that weather stations that are today in Europe. I think we had used this number in.
This is just
500,000.
This is just what
the weather just for measuring wind speed.
Yeah, then I have to switch the slide, which I here. This is.
Is there a tendency from the weather services to increase rather than going to wind farms, just to increase the number of measurement points?
I mean, as I said, there is increase, and that's what when I showed at the end, the additional data sources which are coming. So there are always more satellite, but now also more remote sensing going from the surface up with this in this Toprov project. Also then more. Also, I didn't show more from radar data, additional the 3D, the radial winds. The 3D, so that's lots of data which is coming, which will improve, but still, as I pointed out several times, it's difficult to include it in such a way that you can really see it then in the forecast in a few hours. That it's not just some perturbation on the initial state, and then it's then there are gravity waves generated which propagate out of the model, and after a few hours you don't see a difference to having them or not having them. So that's the difficult always, to really to use them in a way that you really can see it.
I would just like to make a little comment, because one of the things that people that don't work with models don't realize is that the idea of using such data is great, and I have also been an advocate of this, but we have to realize that there are maybe soon 1 million measurements going into a data assimilation. So if a model gets 100 extra measurements, it makes no impact. But saying that, it doesn't mean that we should follow this, because what the wind turbines can provide, if we get a standardized measurement out of it in the future, is something that the community, the industry is interested, and that will also improve the wind predictions in the levels where it's required. But it will mean, strictly speaking, for the modelers, for the MET models, it will mean that we need this on a global basis, not in one country 100 measurements and 200 measurements there. This is not going to give an impact.
The question is how much data you have to add to see a difference.
Just to follow up what Helmut was saying about the new data sources, we're experimenting with those, but it's mostly radar data, which you have to put in with 4D variational data assimilation to get the benefit. And as Helmut nicely showed, it tends to be in what we call the nowcasting period, where you get most effect, and then it tends to be lost. So whether it will make that much difference to, say, the day ahead forecasting is still very much an open question. I also agree with that. The thing that stops data assimilation people putting anything in is the quality of the data. They will not put data, they won't use poor quality data. And that's, I think you've illustrated that nicely here. It has to be very good quality, standardized data. They have to understand the errors in that data before they'll do anything with it. So not just saying you've got lots of data, use it, is not good enough.
This is just an extra slide which I just want to point out. Actually, the wind data which is used, the SYNOP, the near surface wind data which is used in the global data assimilation. You see here, this is on the left, you see the SYNOP observations. And then if you look at the 10-meter winds, because the 10-meter winds we take over the seas or in the flat terrain, or because there we know a bit, there's not so much orography. So there it can be used. But if you go to further inland where there's orography, it's so locally influenced, it's not representative for the resolution of the model. This is now for our global model. So then we cannot use it. The errors are too big, and it cannot be used. That is just an illustration. So this here on the left, you think, oh, that's great everywhere. We have lots of observations. But then you look at the wind there, there's not so much left over. This already looks different. Still saying on the left, as I said, the pressure is probably used at most of these stations. So there are some data, or lots of data is used here on the left slide, but not the wind, 10-meter wind. It's just an illustration. So it's difficult to, as I said, adding data, it's a difficult thing. That's why I also want to tell you here that I would say the Weather Service, they are interested in getting in more data. They also want to do it. But I think from the outside it often looks like the Weather Service, they are not really doing much. It takes so long, but it's a complicated business. Therefore it takes some time until you really see that from a research state, that's saying it's involved. You can make some research programs or some runs to test is there influence of the power, if you have wind farm over the sea, is there influence of the weather? Okay, you may see it, okay, but then still, until you really have it in the weather, in an operational model, running each day for all kinds of weather situation, running under time limits, you have to finish the forecast limit time. you have to finish your assimilation only a few hours after actually you observe this. And this is just takes some time and you really go through the whole process. So it's not that the weather service don't want this. They want to cooperate, but it just takes time until you really will see it.
There should be a good correlation between the improvement of the performance we saw during the years and the increase of the data that you are progressively using. No?
It's increase of data, improvement of the models. I mean, model physics. You've seen on one of the first slides how when we introduced our new model, how we get a big improvement there. But to develop a model takes also years, new models. So it's not something which you can do not even every 5 years. So that's such big jumps is not a normal thing.
I think we go on with the questions.
Miri Kurt from TenNet Bayreuth, Germany. You already addressed the problematic of the offshore wind farms, the installed ones and also the planned ones, which can have influence on the numerical weather predictions. And it has already addressed that it may have an influence already in north of Germany. The next question is that maybe this surface has an influence already in weather predictions, and the orography may be seen easier than the onshore conditions. But as far as I know, the power forecast for the offshore wind farms is worse than the onshore ones. Please correct me if I'm wrong. What kind of activities have German Weather Service concerning offshore numerical weather predictions?
We have no special things for offshore compared to onshore. I mean, also we don't do a power prediction. We do weather forecasting and we predict wind. And then somebody else takes our wind there to make power predictions. We're also naturally trying to improve, you can say, the forecast over the water. I mean, it's a different service. There you have the roughness depends on the wind itself, so it's a bit different, the physics. Then you have a constant source of humidity. So there are naturally differences between weather over land and over the sea. So we have to improve our knowledge, our physics, but we don't do anything special for its power forecast over land or sea. As I said, we don't do power forecasting ourselves. And when we have to include that in the models, I don't even say that we have to include it to really, with the purpose of doing the power forecast, to do it as precise as the clients want it. I think maybe it's rather that we have to represent the wind farms in the way they influence weather, which means that maybe not all the details have to be there, and not the power has not to have the same quality as from somebody who does real power forecast, but the effect of the flow, the reduction of the mean wind, the increase of turbulence, this we might have to, or probably at some time we have to include, because then it will influence also how cyclones are filled up, and then it will influence the weather. That's what we have to do.
That means there's no activity concerning offshore predictions, concerning the conditions offshore.
I mean, it's, in Germany we have these now more measurements, these Pheno platforms there. So this offers also the opportunity to compare our model with the observations, with these observations, where before we didn't have observations. So in this way we should improve, because we now have more, we can learn more about the different conditions. And naturally, as I said, we will look into this now more, but otherwise there are no, as far as I know, no special program saying offshore compared to onshore from the weather service.
So, and if you don't have any urgent, you also get a last question. But that must be the last then, because we need to get ahead in the program.
Okay, thank you. I'm Alfonso Callado from the Spanish Meteorological Agency. Okay, thank you very much for your nice presentation. Okay, no, I think you have addressed two important key points. Okay, one is the high resolution of the forecast with the new generation of the models. One of the important things is the horizontal and the vertical resolution. Sorry? Another important point is the orography for winds, because you are very close to the ground, okay? Don't worry about, it was a question there about the verification, the classical verification with these high resolution models, it's worse. If you make a more advanced verifications, they take into account the spatial patterns, they verify quite better. Probably if we want to make forecasts with these models in a wind farm, we have not take just a one wind information. We have to take an area, several points with output information of our models. So we have to work in areas, not just in the points. Now, doing that, these models verify quite better than low resolution models. For me, the second key point is the use of ensemble prediction systems with high resolution models, okay? Because the uncertainty increases a lot with these small resolutions, and the only way to address that now is using the ensemble prediction systems. So to make a good wind forecast, you need to know about the uncertainty of your forecast. That is another key point. And the only methodology we know to address that is just not to run only a one high resolution model, not running a lot of them, okay, and combine the information of all of them.
Yeah,
thank you very much.
I agree with what you said.
Okay, thank you for the short answer. And with that, now that we've learned how difficult it is to actually run an operational weather model for a whole country and improve weather for everyone, not just for our small community, we're getting into the community and getting into the difficulties to actually run a power system with a lot of wind based on the forecasts that are available. And I'm happy that Ana Rodriguez from Red Eléctrica de España, from the local TSO, was willing to give a talk here, to give a keynote and tell us a bit about the Spanish view and the TSO view on things.
Very good. Let me, while she is preparing, I forgot two practical details. One, the toilet is just behind this wall, so you just go there and there is a door, and the toilet is there. And the Wi-Fi password is on that small, I don't know how to say it, but the small card that is just in the entrance. And those who don't have a badge because came late, there are badges in the side table at the entrance. And if your name is not there, we can improvise your name. And this is important for lunch because this allows us to discriminate the ones who deserve lunch from the clever entrepreneurs that will try to get lunch without deserving, okay?
Well, good morning, everybody. My name is Ana Rodriguez, and as Gregor said, I work in Red Eléctrica. I've been working for 10 years there in a department that is called Forecasting and Load Scheduling systems department, and well, we are in charge of the wind and solar forecasting systems. So today, the purpose of my presentation is showing you our model, our algorithm, and our forecasting system, and also give you the main challenges that we had to cope with this kind of energy. Okay, so firstly, renewable energies. Is this new in Spain? Not really, because at the time of Don Quixote, we have all these windmills, and well, but now we have also giants. We had this kind of giants. We had all these wind farms. We have a lot of wind farms around the country, so we have to cut with this energy. Also, Spain is the sun paradise, really. And I don't know if you are going to have time to visit some of our beautiful beaches here in Spain. But well, apart from sunbathing, we use it in order to obtain electricity energy. So well, now I'm going to focus on. We have a great amount of renewable energy. Here I want to give you some figures about that. This is the installed capacity and the demand coverage in Spain in 2015. As you can see, we have more than 50% of renewable energies in our installed capacity. 22% is from wind, and more or less the 7% is solar. In terms of demand coverage, the figures are almost the same. We had more or less 50%. This is the renewable energy that we have in demand coverage. More or less, the 19% came from wind, and the 7%, 5% from solar, really. So we have a great amount of wind energy. So we have to do something with that. And well, this is the installed wind power capacity evolution in Spain. As you can see, that all began in 1996. Between 1996, we have a great amount. We have to integrate a great amount of this kind of energy in the system. Now it's true that for the last 10 years, the installed capacity has stalled for the last 3 years. So well, but we have 22,700 megawatts more or less in the system. That is a very huge quantity. In the graph in your left side, I want to show you the geographical distribution of our wind farms. They are really in the north of Spain and in the east. So well, and as you can see, there are some points where we have a lot of energy in the system. Well, yeah. Here I want to point out our last record in wind generation. This is the moment of the maximum wind production. It was in last January, and we reached 17,500 megawatts. This moment was at 7 p.m. It was a peak hour, and it was really good because for us it's good to have a lot of wind energy in a peak hour. Normally, this kind of records are around the off-peak hours, but in that case it was at 7 p.m. and we have 44% of energy came from wind. It's very huge, and we integrated without any problem. So well, now well, with that great amount of renewable energy, we have to do something about. We have to do something. And what we do? What we did, sorry. We create a control center of renewable energies. It was the first control center of renewable energies in the world. And well, with the control center, we achieve a greater level of integration of renewable energies. There in the control center, we supervise and control all the real-time measures. And well, but not only the real-time measures are necessary to control the system, to operate the system. We also need a forecast. So, and at the same time, well, I think that it was before the control center. We develop a tool. We develop a forecasting tool, wind power forecasting tool that is called Cipreólico. With this forecast, we can forecast each wind farm in Spain, and we have a forecast for up to 10 days horizon. Also, we add this individual wind farm forecast in order to obtain a national hourly forecast. The prediction model that we use is based on neural networks. We have one neural network for each wind farm. So more or less we have I think that we have 845 wind farms, something like that. And we have the same number of neural networks. So each hour we calculate more than 800 neural networks. So it's a great amount. Also, we have probabilistic wind power forecast. We use these confidence intervals in order to obtain the reserve in the system. So, well. Okay. We have a tool, but we need some input data. Our essential input data is meteorology. We use the numerical weather prediction models, and we use the grid results, really. We have all the grid results of the numerical weather prediction models, and we search the point nearest to our wind farms. So, as you can see in this map, you can see the location of the wind farms that are in green, and the points that we use for meteorology. We use the wind speed and the direction forecast. Here you have the grid that we use in the Canary Island. Really, we don't in Canary Island. We don't use 1 point for each wind farm. We use an average of points in order to obtain a better result. Okay, so well, but we think that this forecast has to be improved in order to obtain better results in our wind power forecast. Okay. Well, other of the inputs of our tool is the input data, but we are not really worried about that because in CECRE we receive almost all the measures of the wind farms and of the solar installations. So the generators have to give us certain measures of plants with installed power that are more than 1 megawatt. Okay, so for wind power we have the 96%. It's very huge. 100% for the CSP. CSP is the solar technology that in Spain we are the world leader well, I don't know if now we are the world leader because I think that Americans are also increasing his installed power. I don't know really, but well, a few years ago we have 50 installations of CSP. That is a great amount. I think that is 2,200 megawatts, more or less. So, well, we have all these brands telemeasured. The problem that we have with telemeasure is not a problem, but it's really difficult to obtain that is with the photovoltaic solar power, because they are very distributed in the country. So only we have 700%, and normally these installations are less than 1 megawatt. So that is the point, that we don't have that. Okay, that's the reason. Sorry. And well, all these telemeasures are supplied as an input for our forecasting algorithms. We use these telemeasures. We introduce these telemeasures in our forecasting system every hour. So every hour we have an update of the measures. Okay. Okay. Yeah. Well, here I want to give you some details about our forecasting tool. We have an on-site prediction model. As I say to you, we use it is based on neural networks, and with that we obtain a forecast. But really, our strategy in wind power forecast and in other forecasts that we make, is a combination strategy. We don't have only one forecast. We use different forecasts. So normally we have 3 or 4 forecasts that we combine. We use a combination. We have a combination model that works really good, because in the graph that you can see here, you can see the results from 2015 of the 3 forecasts that we combine, and the result of the combination. Always the error of our combination obtain an error less high than the other ones. So we think that this is one of our best improvements in our tool. So regarding errors, here you can see the evolution of our wind power forecast errors. You can see that we improve significantly in the last 8 years. This is from 2008 till 2015. You can see that the last 3 years we are reaching our top, really, because now we think that it's very difficult to improve our model, to improve our mathematic model, really, our neural network. We think that we can improve our forecast if the weather prediction models improve its results. But well, let's see. So I want to point out that this is the errors. This is the mean absolute error relative to average production, because in other, I don't know, it could be done in other speeches. You can see these errors, but relative to installed power. If we do that, we have a great amount of installed power, so the error can be less. Can be short. Yeah, no, sorry. Okay, so yeah, well, but although we improve our forecast, we obtain lower errors. There are some days that it's not easy to make a forecast. This happened last 9th of May of this year. Here you can see two curves. The first curve is the yellow one, and you can see the real production of that day. That day we have that production. And the green curve is our forecasting for the day ahead. Okay, we made this forecast the previous day. Okay, and here you can see two main difference between our forecast and the real time production. The first one was between 3 a.m. To 6 a.m. And we have more or less 1,500 megawatts of difference. Well, you can see it's really huge, but really this was predictable for us. Because at the same time that we made this, the forecast for the day ahead, we know the price in the electricity market. And we know if the price is under this euro, this euro, 10, I say the French, sorry, 10 euro, yeah, 10 euro, the generators are not going to produce. So although we forecast the energy that they are going to produce, this is not going to happen because in the electricity market, the price is under 10 euro. Okay, so we warned our control center with that data. We warned that it could be in that tower, the prediction that we made is not going to be that. So it's predictable for us. It's not in the forecast tool. We are not introduced this issue in the forecasting tool, but we know it. Okay. The difference that we are really worried is the other one. The difference between more or less 4 p.m. and 9 p.m. We have more or less 3,000 megawatts of difference, and it was not predictable. It was due to storms that happened in that day in Spain, and there are some storm cells that a prediction model can forecast. So there are phenomena that happen very fast. So we had this problem with the wind power, with the wind speed and direction forecast. This is one of our main concerns really now in terms of wind forecast. So well. We are always working on. We improve our forecast year by year since the Cipreolico application was developed. But our main challenge now is improving our forecast for that kind of days because our mean error is really low. So, but we have this problem with that singular days. So our wish list really is trying to use a neural weather prediction with higher spatial resolution grid. Now I think that there are two models developed, two numeric weather predictions models developing. One is I think that is called Harmony or something like that. I think, yeah, it could be the IMED could tell me. Okay, and the resolution, the spatial resolution is going to be higher. We are going to try higher spatial resolution. Let's see if we can use that to obtain better results. But we think that the main point, or the thing that we think that is going to help us is increasing the alert frequency, because I think or we think that the problem with that kind of errors, that this is because we don't have enough update frequency of this forecast. We have now, I think that is every 12 hours we receive updated of the forecast. So if we have this updated every 3 hours, it could be that we can predict that phenomenon. Okay. So now we are we are going, we would like to work in outcasting. I think that next year we are going to work with our agency, meteorology agency, with IMET, in order to do a project, an I&D research and development project about wind forecasts that could include these storm cells. We think that with the nowcasting we are going to be able to forecast that. Let's see. It's one of our wish list. So that brings me to the end of my presentation. So thank you everybody, and if you have any question, I will be glad to answer them.
I would like to ask, thank you for the presentation. It was very, very nice to know what are the advances in Red Electrica. We are following since many years in collaboration in different projects. I would like to ask, in the slide that shows the improvement throughout the years, does this refer to the average improvement per wind farm or to the average?
No, it's the average of the national.
And it's not a bit tricky because this improvement is to a high degree thanks to the smoothing effect, because as installed capacity increases, of course you improve.
But that I mean, these errors are relative to the production that we have in our system, and normally the production in our system is more or less. I think that. For the total of installed capacity, we produce 70% of the total amount.
Yeah, but still, if you want the process you try to predict is not the same. I mean, if you have a high number of wind farms, you reduce variability.
Yes.
So even if you normalize by average production, we have always seen some improvement in the results. So I think it would be interesting to take out this effect by doing a kind of average evaluation per wind farm and see what is really the effect of model improvement.
We do that also, but I don't have the figures here. But we analyze every wind farm, and if we obtain a higher error, we try to know what is happening with the neural network, because we know that it could be the wind, it could be that we don't use the point. We do it, but I don't have the figures here, and I can say you the I don't know the error that we have for each wind farm. I don't know really, but we try to.
I would like to see maybe in the next presentation.
Yes, could be.
What is the evolution of the error per wind farm during the years?
Yeah. Okay.
This would be nice.
Okay.
Thank you.
Because I already have. Thank you for your presentation. It was interesting to me when you said that your system makes forecast to 240 hours. And that just before I had said, it seems to me that the day ahead is the most important. So actually, how important is it?
Not for us, really.
You really, the 10 days, and you want to do this every 3 hours, new forecast?
Yeah, no. I'm going to give you more details about that. We made a forecast, a wind power forecast, each hour. Each hour we made our forecast. We updated with the real-time data, okay? The problem is that, well, here you can see in the errors, you can see that here for the first 5 hours we have less error. This is because of our update of real time, okay? But here there are the error really that comes from the numerical weather prediction model, okay? We only update that kind of information every 12 hours. So for us, we make an forecast each hour, but only every 12 hours we obtain this updated for the wind speed, okay?
But you said you make it to 240 hours forecast, 10 days.
Yeah,
How
yeah.
is the 10 days compared to the usual 2 days?
Okay, sorry, I don't understand your question. Yeah. Well, this is because we are more worried for the first 2 days, because it's the forecast that use our control center. It's true that we make forecast for the 10 days, and it's due because we use this forecast in order to other things. We try to schedule our work planning in the grid. We had the system and we had to schedule this work planning. So we also have to know the forecast for all the 10 days. That is the okay, sorry.
Joe Warrington from Baringa Partners. I have a question about, you said that knowledge of the price is sometimes helpful for predicting.
Yes.
Do you have any plans to incorporate price in your models?
Not really. Why? Because there are not a lot of generators that do that, because here in Spain the generators company go to a pool, okay, to a market pool, and in that market pool they can do a lot of things. If they have in their portfolio, they have wind, but also they have water, they have a hydraulic generation, they are going to compensate that energy. This phenomenon, there are only few generators that they are only had wind. They are only these kind of generators. They are the only that do that. So introducing our forecast that kind of information, it could be tricky. I don't know how to say it. Tricky could be, okay, because there's something that we don't know what they are going to do. We don't know really what amount they are not going to produce. So it's better to know that it is going not to be the perfect forecast that introducing our model. Okay.
Milko, TenneT Germany. You said that you have over 90% wind, 70% solar directly connected, and you are getting online data. It's a dream for Germany, for German TSOs, and it will not be realized in the coming 5 years, maybe, that we get too much online data. My question is that having so much online data is for sure an advantage for the statistical models.
Yes.
And you are using neural networks for each single wind farm.
Yes.
If you have a new wind farm for the neural networks, you need historical data.
Yes.
How do you solve this problem?
Well, really, now we are not so a great amount of wind farms that enter in the system, because but if there are one wind farm that enter in our forecasting tool, what we do is we know, because we don't have every wind farm telemeasure, but we know the install capacity of the area that we are going to forecast. So we make really we deduce the wind power that wind farm that we don't have any data. We forecast with an to say it, I don't know how to say it. It's that. Yes, we have to do upscale. I mean, if we have one wind farm that is close to the wind farm that we don't have data, we think we upscale with the install capacity of the wind farm. Okay, We know the production and the capacity of one wind farm, that is telemeasured, and we don't know we only know the installed capacity of the other wind farms. So we make a regla de tres, I don't know in English how to say that. Okay. Yes, okay.
Thank you for your presentation. This is a question in relation to the previous one and to the first presentation. You talked about 800 neural networks. I was wondering how you do recalibrate all those neural networks.
Okay, yes.
And the problem of the first presentation was about the quality of the data. How do you control the quality of the real-time data?
Well, for the first question, sorry, was about, sorry. Okay, yeah, about the models. Okay, yeah. We every month we know the new wind farms that enter in our system. So at that time we made a recalibration of our neural networks. So we do it monthly, really. Okay. And the other one, sorry, today I'm not very. I don't have a lot of memory.
The second question was in relation to the first one about the quality of the data, because you need good data to recalibrate.
Yes. Really, we have all the serial data. Okay, all the data for the historical data, and we see if there are some measure that is up of the mean, really, or is a measure that is not good, and we I don't know, no sé cómo decirlo. We erase that data in order to do the recalibration of the Pablo. No, sorry, because yes, it's my boss and he could be more accurate.
Sorry, well, just for answering the second question, yes, we are calibrating by means of energy meters. So really, we have about 96% of energy, with tele measurements. But what we do is just to test the quality of our estimation. We have to estimate the 4%. What we do is just to compare the energy that we are estimating by means of comparing with the energy meters. And we can do it every month, and as Anna said, we do it every month, and that's what we do. So more or less the error, the average error is close to 2% or something like that. Yeah. Which is more or less noise, taking into account the amount of energy that we are forecasting.
Yeah. So the telemetric data that you receive from wind farm operators, are you also receiving an outage plan, or do you have any idea if a large wind farm will be out of operation for whatever?
Sorry, I don't understand.
So wind farms aren't operating 100% of the time.
Yes.
And often this can be a planned outage. You're doing repairs on the turbines, for instance.
Okay, yeah.
Is that something that you're notified of?
No. I mean, we receive the total amount, the total production of each wind farm, but we don't receive every single aerogenerator, okay? So if one of the aerogenerator is in maintenance, we don't know.
How does that affect? I mean, that affects
your,
the quality of the data. If you don't know the
normally, I understand you. But normally the maintenance, they are planning, and normally they do it when the wind, when there are not wind. Normally they do that. If there is I don't know. Well, if there is something that is not planning, okay, Yes, we have that problem, but it's not really.
Do you get notified of that?
No, not really. Because it's something for the generators. It's something that the generators do. We are not we don't receive that information because it's something internal. So.
Okay. Good morning, Ricardo Bessa from the Inestec Portugal. So you have all these real-time measurements from the wind farms. So did you consider to use the spatial temporal correlation of the errors to improve your forecast?
Temporal correlation.
Spatial temporal.
Spatial temporal correlation for the production.
Yes.
No, it's something
because
that we don't.
You can improve your error. You showed that plot where you see a limit, but you have all this information. If you explore more this information, you can improve your error.
Yes, I think that we thought that in the Canary Island, because there are some winds that they always went go in the same direction, and it's true that in one of our it's true. We saw that it's not also so easy, because we thought that if in one Canary Island there will be a great amount of wind, in the other they are going to have it only some hours after. But finally, with that study, we made a study. We reached that that is not so important. But I don't know. We can try it.
Because we tested this in Portugal for all the wind farms in Portugal, and it improves a lot up to 10 hours ahead.
Okay.
Of course, the distribution of the wind farms in Portugal are more concentrated, not like in Spain.
Yeah.
But you could probably do by region, South Spain.
Yes. The problem that we had is that the wind is very local. The wind is very local, so I don't know if it could work. I don't know, but this is a good idea. Thank you.
Okay. Just one final question is about, you mentioned the probabilistic forecasts. Do you generate them with the statistical model, or it is a weather ensemble?
The
probabilistic forecasts?
Yeah.
You generate them with statistical?
No, we obtain that forecast for a supplier. A supplier give us this kind of forecasting. Because, we know that this supplier use the different ensembles, okay? But we don't know how it.
Okay.
Gracias, Ana, por la presentación. You said that to improve your forecasting system, now probably you need an improvement in the numerical weather prediction models. So my question is related to that. You are using now just one only numerical weather prediction model, several of them?
We have two.
Two, okay.
Yeah.
And later, what are the resolutions of these models you are using currently?
Well, the resolution now I think that is 12.5 kilometers of the square of the grid, okay? For one of them, and the other I think that is almost the same. It's more or less the same. It's true that we have a project in the Canary Island in order to reduce this spatial resolution. But it's only a project. We don't know if we are going to have better results. But yes, we are going to try to reduce our high spatial resolution, okay? No?
A question about...
Why? Yeah, I know. Ireland is... Yes. Yes. Yes, but today is not a... Yes, we know. It's 2.5 kilometers, yeah? Mm-hmm. Yes, yes, but I think that we are going to improve in the horizon nearest to the real time. But for the 10 days, we think that we are not able to use that kind of prediction, okay, the forecast. Yes, we have to try that, yeah. And we think that we are going to use that, but it had to be in operation, because now I think that they are in. You are not in operation yet, I think, no? Sorry? Deterministic, yeah? Yes. You have that, yeah, now? Yes? See? Ah, okay, thanks, okay. Okay.
About the probabilistic forecast that you mentioned, I would like to ask how do you use them, in what kind of process? Because often in power systems, you know, they are not really integrated inside the different tools like unit commitment, dispatch, or any other. Do you use them, and in what?
Well, yes.
How have you integrated them in the process?
Yes, we use it for calculate the reserves of the system. Okay. And now the algorithm to calculate this reserve has changed in Red Eléctrica. I think that now they use a probabilistic also a probabilistic algorithm to calculate this reserve. They use the probabilistic wind power forecast, and they make some probabilistic functions, okay, in order to calculate the reserve. And for that is in the mainland, in the peninsula, okay. But in the island, in the Canary Island, we use our probabilistic forecast in a unit commitment, because in the Canary Island we have a unit commitment. We don't have a market, electricity market, okay. So we use that.
Okay, I got a few questions. I got a few questions from the remote audience. Some of them are a bit technical on the numerical, on the neural networks. One is, are you testing other artificial intelligence techniques such as support vector machines or genetic algorithms or any hybrid models or so?
Yeah. Well, I think that one of our, because we have not only our forecast, we have other suppliers. I think that one of our suppliers is use that. Yeah. Yes.
Okay.
But it's true that the algorithm, there are not only one algorithm that is the best. So we try to mix.
There's another question from Martin Felder. Do the neural networks for each wind farm predict the 240-hour forecast in one pass? So with 240 output neurons, or is the forecast step through?
No. We don't have one neural network for each hour. No, we obtain we have one neural network, and we obtain the 10 days forecast. Okay.
Okay. I have a question from Jan Bert Schröer, which is how did the price in that example of the 10 euros per megawatt hour actually get that low? Is that because of higher production of conventional power plants, or is that the day-ahead price?
Yeah, that is the day-ahead price, yeah.
Okay, so it's in principle easy to integrate it, at least conceptually.
Yeah, conceptually, yes.
Okay. And there were a couple of more questions for the solar forecasts. Are you actually using cloud coverage forecasts?
We use cloudiness, yeah, for the solar, yeah.
But do you actually use sensors for that, sky images or infrared radiation?
Could be my boss could answer you better, because he's more in solar generation. Okay.
Please, could you repeat your question? Sorry, you were talking about the cloudiness. Yes, we are using the cloudiness, of course. What we are doing is just
the sky.
We are starting a new project with IMET, our national MET agency, in order to improve our what we call nowcasting, because we are concerned in the first 2 or 3 hours, and we are developing a new model based on satellite images in order to combine with a wind forecast model for the first 2 or 3 hours. Well, we are waiting for the results, but we are really worried about this, especially in the islands, because, for instance, in the 2 or 3 hours, we have a lot of installed capacity in Tenerife or in Gran Canaria, and the problem is that the generation change very quickly, and we have to forecast this in advance in order to calculate or to adjust the reserve of the power system.
Are you using ground-based sensors for that too?
Ground-based?
Like
cameras?
No.
Sky
no, because this must be done, I suppose, in the installations, in the farms, no. So it's not really. We prefer to use satellite images in order to do that. No? We know that this is an option, of course.
Mm-hmm.
There was one more question there was one more question from Kali going. Do you actually use any more measurements from the wind farms, or is that just power measurements?
There are only power measurements.
Okay.
I also have a question to the measurements.
Yeah.
How much you said that you have 100% of the CSP and 78% of the PV. How much household installations do you have, and how are you dealing with this? Because that's a problem.
Yeah, we have more than, I think that it was 50,000 installations, I think, in Spain of PV and PV. But the thing is that they are a group, okay, in order to give us the measures. So is that why we have the 70%? Okay.
But it means that you don't have measurements for the households, right?
No, not for
it's the same as everywhere else.
Yeah.
But do you have any plans of how you can use?
I don't know because I don't know really, because we think that autoconsumo, no, Pablo, no. It's a different question. Okay. So no. Yeah.
Yes.
The question is that.
Yes, they aggregate.
Kind of things. Our idea is that we don't need anything else in order to improve our estimation, because I think that we are one of the countries in the world with more amount of, with the highest percentage of PV forecasted from the operator of the system.
Yes, I agree, and I can also see that 55,000 installations for households doesn't seem to be too much in comparison to Germany, that has 1.4 million installations and no measurements.
Yeah.
Because it's of course something that comes as negative demand, but
yes.
In Europe at least there is a kind of a plan of a rollout of telemetering or of any kind of electricity in the households. And one of the discussions we have in Germany at least is that how can we actually get hold of this information, because it is it has an impact on the grid, and it has also a negative impact on planning the grid. So I was just wondering whether there is any kind of thoughts or plans in RE to deal with that. Okay, thanks.
One question. I know that in the past you used different models that were developed in collaboration with Carlos Free University.
Yes.
And then combination.
Yes.
Now you mentioned about external providers.
Yeah.
Now, do you use your own models that you had at that time plus external providers and you combine, or just external providers?
Yes, the combination is only for the national forecast, okay, not for each wind farm. So there are suppliers that give us this kind of forecast. Yes.
For the national?
For the national.
Okay. And they are based on kind of total power or individual wind farms?
Yeah, they are based on the total wind power.
Okay, thank you.
So I think we went through 2 excellent talks and excellent discussions, and deserve a coffee now, which is outside, luckily. And it's been nice to see that we actually have gotten the possibility to have a feedback channel from the outside participants. I think that's a good thing. And then we'll convene here again at past for the next round. Thank you. See you then.
It doesn't work. Now, okay.
I wanted to ask, can I get the presentation?
Sorry?
Can I get the industry experiences. So we got 3 talks from a German TSO, from a trader in Germany, and from a French wind power operator in how they actually use the forecast. And the first speaker is Mili Kurt from TenneT in Bayreuth. Please.
So, good morning, and I think we are all fine after the break. Thanks for the organization and for the possibility to present the challenges of integrating wind power from the point of view TSO. I will present first of all development of renewable energies in Germany. I will explain the general challenges we are facing, and I will go a little bit deeper in wind power, give some examples concerning cutoff problematic and in-fit management, and finally I will explain about showcase projects in Germany. So, information about the company, I'll keep it short. TenneT is the first cross-border transmission system operator in Europe, in Netherlands and Germany. We have, okay, do we have light? Okay. For me, no problem. So, in total, we have 21,000 kilometer high voltage and extra high voltage grids. 12,000 kilometers is in Germany, including 1.4 thousand offshore connections. And we are serving over 41 million end user consumers, and in Germany it is approximately 24 million. And as a TSO, our main task is to construct new grids and maintenance of them, so that we can transfer the big size of electricity to lower size grids and to big industrial consumers. So, as the key task of a TSO, the first one is the transmission services. As I explained, we are responsible for the construction of the grids and maintenance of that. We are also responsible to ancillary services to keep the balance of generation and consumption 7 days, 24 hours in our control zone. And we are also promoting the markets to get the stable and future development of the electricity markets. This slide shows the development of renewable energy sources in Germany, and based on different scenarios done by the Ministry for Environment. As you can see from the plot, this is an increasing development year by year. And the yellow one is the solar, the blue one is the wind, the green shows the others. And all of them are increasing in all the different scenarios. And if you look year 2016, we are all over 92 gigawatt installed capacity in total, all renewable energy sources. And the load for the Germany varies between 25,000 megawatt and 85,000 megawatt. That means our installed capacity is already over than the load in Germany. For sure, that brings new challenges and everyday issues for a transmission system operator, or in general for system operators. And the goal of the German government to improve the share of renewable energy sources in gross electricity consumption to 35% in 2020, and for 2030 it's 50%, and for 2050 it's 80%. It was in 2015 already over 32%, the share of renewable energy sources in gross electricity consumption. The changing thing is not the installation of the renewable energies in the system. There are different parameters or players in changing always, and they all have influence on the power lines, power grid, and integration of the renewables, concerning the renewables. One of them is the politic. I have never seen a stable politic. It doesn't match with the politic. It's not stable. It cannot be stable. And it is changing always. The law is changing. The support mechanism is changing. And for sure that plays in the installation of the renewables a role. And also for us an issue as a transmission system operator. The market behavior in Germany is if you have a wind farm, solar power plant, you have two options to sell your energy. You can directly market in the exchange, or you can get a fixed tariff over transmission system operator. You have no risk for the trading. You are getting fixed payment. But this is always changing, always coming new rules, and the power plants operators have the options to change from one to other, and it's always changing. And also the population is changing. The people are moving. It's in a discussion all Europe is in, for example, the refugees. Maybe it could be an influence on the power supply and the development of the grids, which will be considered on that. One specific problem is the solar self-consumption. This is we are talking about millions of solar panels in Germany, and each single one have its own profile, and it plays a role for sure in the integration. Another issue is in storage for the households. They are using and they are going to use more storage systems in their houses, and also electromobility, the electrical vehicles will be also part of the grid, and it will be an effect on the system. The most known is, I think, in this group is the weather. It's quite volatile, both solar, wind. It's a big impact of the integration of renewables and also power grid. So we are going a little bit deeper to RES production in control zone of TenneT. In total, we have 41 gigawatts renewable energies in our control zone, more than 15 gigawatts solar, over 20 gigawatt wind onshore plus offshore, and yeah, so 8-9 gigawatt the others. And it is the largest share of renewable energies compared with other transmission system operators in Germany. It is over 43%. But we are marketing just 32% of that. It's a responsibility of transmission system operator in Germany to trade the renewable energies also. There's a mechanism that is organizing the balance between different transmission system operators to share the load of the integration of renewables between transmission system operators. That means if there's a higher consumption in a region and a higher production in another region, that must be shared to find a balance, the overall load to share between transmission system operators. We are trading in different markets, in day-ahead markets, intraday markets. We have also the trades over the counter. We have to interest mainly integration, security integration from perspective of security of supply, and also to improve the market integration of the renewables. This is you could see from this plot also, this graph also is this, the similar one. Just expand with the Netherlands part on the left side. The TenneT TSO is from north to south Germany. It's like a corridor for the whole country, and we are facing all the problems which can faced by a TSO. In the north of the country, we have mainly wind power generation. In the south of the country, mainly solar. And but the consumption is also differing between the different parts of the country. You are seeing on the plots on the right side the wind and solar generation in the north of the country. The blue one is the wind, and the yellow one is the solar. The wind power generation is quite higher, clearly, and it is the plot bottom there is showing has an opposite one. This is the solar production is quite higher than wind production, and we have to move this energy from south to north or the other way, and the result is congestion of the grid. The grids are not ready to transport this high volume of energy, and it is necessary to improve the grid capacity. This is a very interesting a graph for me. The challenges of the integrating renewable energies in Germany, I think there's nothing better image which can show which difficulties we have before and after Energiewende decision of German government. Energiewende is the energy transition from the nuclear to renewable energies in Germany. It was decided after Fukushima, and as you can see from this figure, it shows the inverted tensions in our grid from beginning 2003 till 2014. And here this line, dotted line, show the nuclear phase out. And the numbers here, the first one is the number of the interventions, and the bottom one is shows the days. In 2003, we had in 2 days just 2 incidents, but if you look at 2014, we had every day. I think this number is not correct here. It is too much here. I have to check it, validate that. Yeah, okay, that could be correct, yeah. And if, more or less every day, more than 3, or more or less 3. It is the reason of, for sure, the change of the power generation. It's not anymore centralized. It's now more decentralized generation. And the load flow is now different than before. And we have more volatile producers than the conventional ones. And that brings some needs concerning north-south connections, and as it can be seen from here clearly, the count of the interventions increasing dramatically. Yes?
What form do these interventions take?
That contains the all possible interventions, in-fit management, redispatch, they're all of them. For the all grid components. So that's an also interesting picture, as I showed before. The generation from renewable energies is already higher than the load, and it's an example from 2013. The blue one shows the residual load, and the green one is the solar generation, and this blue turquoise is the wind generation. And at 25th of March, we had more generation than load. Then that means you also need solutions to keep the grid stable, and you need storage in this case. Maybe water reserves, maybe power to gas. Different solutions are welcome from our side to develop new ideas. And another example is in the same month, end of this month, after just only 4 days after that, we have very high load, but very less generation from renewable energies. And we have to manage that all in our control area. So the next slide is application of REST forecast in transmission system operator. We have, as I said, we have two different interests. In one of them is the system operation, and one of them is the trading. And for both of them, we are getting different forecasts, and we are using different forecasts for both of them. Mainly the same providers, but different data sets, finally. The system operation has interest system stability, congestion management, and forecast of that for day ahead, 2 day ahead, 3 day ahead, and to reduce the need of balancing energy. For the trading, it's interesting for the balancing group, EEG balancing group called in Germany, or maybe renewable energy sources balancing group. And for sure we are trying to avoid unnecessary trades and improve the performance in the power exchange, so that the load of the end consumers will less. Otherwise, they have to pay if we have a bad performance in exchange that is paid by end consumers in Germany. And that all serves for the security of the system operation. We have to keep that, ensure that the N-1 security, if one net component is not working, then that should not result the blackout of the system. That must work. And redispatch is an issue if we have higher generation from renewables. We are dispatching the conventional plants, then we are turning off one, but the other parts, they must be improved to compensate that all. If we talk about the fit-in management, we are talking about the high generation from renewable energies. Then we we have to turn off some renewable energy plants for in this case to keep the net grid stable. These slides show how we use the single predictions in our operational works. Please look at the diagram on the left side. We have different providers for wind, for solar, for different energy sources. We have different providers supplying us the forecasting for intraday, for day ahead, or maybe longer term. And they all use different data sets, as far as we know. And some of them using satellite graphs, all of them using numerical weather predictions. Some of them using directly online data from the power plants, and using different algorithms also. Some of them using statistical methods to make forecasts. Some of them using physical models. Some of them combining both of them, mixed methods. And there are also some, they are supplying us probabilistic forecast. Then an important point also for Germany is an extrapolation. We have for following hours or days, we're making forecasting, and also to calculate the online generation, we are making extrapolation. That means we are not so like in Red Electrica, we don't have so much connected online data. We have to make extrapolation. For some, it's also a forecast to calculate the overall generation. The next step after we get the forecast from different providers, we are combining them. Maybe the providers are using the ensemble models, and we are making our ensemble for us and making meta forecast, a combination of different models. We are considering the historical data. We are using 2 or 3 months historical data to calculate for the best combination of different providers. As you can see here, this here W and F. W stands for the weight of the provider and its forecast here. And for each provider, we are giving a weight. And finally, we are getting a combination of them. And we are taking care about the weather stations. It differs the weights based on the weather stations. We are making also online corrections based on the upscaling values or the online values. And we are using also our experience by the combination. That means that if for a single month we get for a provider very high weight, that doesn't mean that we are applying the weight for the following months. It's sometimes exceptions that happens. We are using our experience for the combinations also. And that all going, as I said, to different operations. For the trading operations, we are using this forecast, and also for the system operations, and also for our reportings, we are using these data sets. And to say the quality of the providers, I have to admit that the quality of our providers is quite good. But there is also still the improvement potential. In a normal day, we have very good predictions. Let's say it's a sunny day. Overall, Germany, there's no clouds. We are getting perfect forecast, and that's matching very good. But it's the case in Germany, not so much sunny days. We have seldom sunny days. It's a little bit cloudy and partly cloudy, and it's being difficult. And if it's the case, fog or Sahara dust an issue in the last years, that's then a little bit critical. As I said, I will just want to show you the difficulties which are facing. One of them is in Sahara dust. We had an experience in 2014. None of the providers had experience before with this issue, and it's repeated in 2016. And unfortunately, the models didn't consider that enough. We had still problems with Sahara dust. Maybe it's an issue also for the numerical weather forecast that should be considered. Solar eclipse, it was in station 2014, 20th of March. It was we had to prepare us very good for this issue, and we did really very good. We started several months ago to coordinate that between 4 TSOs in Germany. Some of the colleagues wanted to take free, but we had control. We could control it. The deviation for single 15 minutes, it was minus 2.7 gigawatt in one direction. In the other direction, when there's again the generation back, it was for a single 15 minute 4.3 gigawatt difference between two in 15 minutes, and that happened in 2 hours more or less. At 10 o'clock we had 13 gigawatt. At 11 it was reduced to 5 gigawatt. At 12 we had 20 gigawatt, and we had to manage that all in 2 hours. This discrepancy between in 1 hour from 5 to 20 gigawatt, and we did it very good. And it was a test for Germany. Is that really possible to manage this high penetration of the renewables in a grid? And we had a very good experience with that, and we showed that it's possible, but not easy. And another issue is in fog for solar, and snow cover is also an issue. Now we switch to wind, influence of the wind in transmission system operators. There are different players here. Also, storm front is an issue. Storm cutoff, especially the offshore wind farms. I will show some examples for that. Icing, another problem. And also in wind management, I will show also some examples concerning that problem. To cutoff problematic, I have an example from 2015. If you look, the plot on the left side, the dark line is showing the measurements from Finno 1 met mast, the first German offshore met mast. And the other line is showing the power generation. It's in the Hurricane Nicholas, happened in 31st of the March 2015. As you can see here, there's a cut off very clearly. This is going down from 1 gigawatt here, or 1.1 gigawatt, to 200 megawatt. And you can see the correlation between wind speed. It's coming to 35 meter per second, and step by step turning the turbines off in this case. You can see in time delay here. It can be explained the all wind farms are not next to met mast. For sure that can be explained, but it's a big issue that must be considered in the forecast models. In this case, occurs the ramps in very short times, and that results the instabilities of the frequency, and has an impact on the system balance. Another example, it was in 2015. It was an interesting year for TenneT. Came over 2 gigawatt new offshore wind farms online. And if you look, the end of 2015, we have 2.6 gigawatt installed capacity offshore. If you look the single days, you can see the volatility. It's very clear. It's not any more discussion. If you look at single day in a very short time, the generation is going from 2.5 to 0. You have to manage that all in your grid. In fit management considers that the TSOs are allowed to manage it's an issue for the grid stability. They can contact with the DSOs so that they turn off the turbines to manage the congestion. In 2015, we paid for that in Germany 1.1 billion euros for infant management, and most of them was in our control zone because we have the most wind installed wind energy in our control zone, and this is the main problem is the wind turbines. In 2015, as I said, it was 5,200 wind turbines with a total capacity 9.1 gigawatt. At least one time they have been in infant management. There's the mainly, as I said, 90% is wind turbines is the issue. And in the coming years, the solar will be also an issue concerning infant management. To process, we are contacting, as I said, with DSO if we need a reduction in the grid. And we are giving this notification at DSO, and they are sending to plant operator. But this reduction, let's say we want here 100 kilowatt, but to achieve to a grid component, this 100 kilowatt, the DSO must reduce too much than 100 kilowatt because of the meshed grid structure. To get this reduction at a grid component, they have to maybe reduce 700 kilowatt to get this for a specific grid component. And the payment is backwards, and we are paying back to plant operators the infant management cases. To manage that, we need better extrapolations of the wind. That means we need more online data from wind farms, and we are collecting also. We are in connection with direct marketers, with operators to get more online data to figure out the reality of the power generation. In this case, we need a theoretical generation and the real generation to calculate the difference of them. An example I have here is quite new. Okay, this must be 2016 here, December 2015 and January, February, March 2016. There are different problems here. The green one is the measurement we get from the DSO, and the blue one is the extrapolation we get from our providers. There's a big difference between two time series. There are different factors they are resulting that. One of them is infant management. The other one is the change from direct marketing to a fixed tariff or otherwise. And another problem is the quality of the reference data, master data. There is also problems, as we heard from the presentation of German Weather Service. We have also difficulties with the master data. It's another example from for the Germany for the trading. The yellow one is the real measurement which we get after 6 or 8 weeks from the DSO, and the green one is the extrapolation, and the yellow one the short-term prediction of them. Both of them are matching very good, but the real measurements which we get after 6 or 8 weeks, there is a big difference of the time series. It's the same problem as I addressed before. To conclude, I have just a few slides. I will do it quick. We have interest for trading and the security of top supply. That's why we are trying to improve the forecast. And we are dealing with high forecast errors. We are detecting sometimes the too late errors, as I saw before, the measurement data and the extrapolation. We need for that new systems which for all our internal processes, which can manage the higher volume of data and give the possibility to use different algorithms. The keyword will be here in this case big data. I listed here the different problems. I just give this explain the solutions. Increase on data quality and data sources. We are collecting different data sources, and we are going to collect more online data. We are trying to improve the visibility. We are building monitoring systems, and we are trying to optimize our meta forecast, and we are improving the spatial temporal resolution of the forecast. And we are going to shorter time horizons. The navcasting models will be interesting in this case. And last part of this presentation is the Schaufenster projects, showcase projects founded by Federal Ministry for Economic Affairs and Energy. Has a volume in total 600 millions in Germany. There are 5 projects. We are, as TENET, involved in 3 of them. C-cells in this project is focused on the solar energy. In NERA and NIF4 0, the main focus in wind. Different issues of the wind, forecasting, extrapolation, visibility, controllability, active power, reactive power, ancillary services, different topics, issues. We are going to work on them. And these are our use cases in different projects, and we have 5 different demo project or use case we defined. One of them is in energy navcasting. The main focus is in the navcasting models to integrate them in power forecasting. Next one is in the flexibility and controllability concerning the ancillary services from renewable energy sources also. A project is forecast optimization, considering all wind, load, and storage, all the players. And another one, direct control of wind turbines, direct controlling by TSO the turbines. And then another one is dynamic reactive power from wind turbines to get a standard market for the reactive power. All our goal is to improve visibility, predictability, and controllability of the renewable energies and other flexibilities. In this case, maybe electromobility also is the topic. I explained shortly this. As to conclude, we have different influences on the forecast and extrapolations, different technical issues and also meteorological issues. As to technical influences on oven consumptions concerning solar storage and in-feed management. To meteorological ones, fog, snow, dust, and storm, different problems. We are using the forecast in our different processes for load flow calculation, congestion management, in-feed monitoring, trading, and after we have the forecast, we are making an online correction, and we are using optimized forecasts for our processes. Thank you very much for your attention, and if you have questions.
For time reasons, we just have time for 2 short questions. Mili is going to stay here for lunch, but has to fly out after that. So over lunch, you have the possibility to go more in depth with that.
Okay, Ricardo Bessa, Funding National Tech Portugal. One quick question is about reactive power. Is this an issue for you? Because the downstream network, the distribution network, will probably.
It's the main issue for the DSOs. You are right, but our interest is to find standardized solution for that. We have in Germany over more or less 900 DSOs, and you need some standards to manage that all. It's our main interest is that.
You don't
point.
have problems in your network with injection of reactive power from the DSO side? Because this is happening in Portugal. The voltages are rising because of that. This is because they don't use forecast.
Yes, this is for sure it's an influence on the grid, but there is not a financial model for that all. That makes the interest less.
Because
but
in
it will change.
Portugal, they pay a penalty for the reactive power they consume and inject. Okay.
Yes.
On a related note, another ancillary service would be synthetic inertia. Is that something that you're looking at the need for in the future? There's no market for that.
Again, sorry, I didn't.
Synthetic inertia, is that something that you're...
Set of inertia.
Inertial momentum, I mean, spinning mass, I mean, when you go to, you have what, 40, I don't know how many % you have of wind, I mean, you're reducing the amount of spinning mass in your system. You can replace some of that with synthetic inertia. It could be built into the grid codes. It's done so in some places in the world. I guess the answer is no.
I guess the same. We can discuss later on to maybe you should explain a little bit deeper to understand the issue. Then we can discuss it later on.
In the grid code of Germany, there is this possibility of inertia emulation from the wind farms. I'm not sure. But even for that, you need forecasts to know how much wind and inertia you have in the system.
That should be the case.
Yeah. Okay, then I would say we close it here, and you have some discussion coming up, I hear. Thank you very much. The next speaker is Efi Gogolu from Statkraft in Düsseldorf in Germany. And she'll present us the trader's point of view.
So, hello, I'm Efi Gogolu. I come from Statkraft, Germany. I will present the significance of the forecast in the short-term power trading. I am not a trader myself. I am responsible for the forecast we get, and I work closely with the trading teams. So, Statkraft is one of the Europe's largest producers of renewable energy and a leading power company in Norway. We are a European leader within renewable energy. We are Norway's largest and the third largest power producer in the Nordic area. We have core business areas within hydropower, wind power, gas, district heating, solar, and we are a significant player in the European Energy Exchange. So Statkraft Markets serves as a centralized hub for trading for Germany, Austria, France, Belgium, Netherlands, Switzerland. And one of our core business is trading and sales of electricity, fuel, CO2. And we have a list of customers with distributors, traders, industrial customers, and power producers. And the operation of these power stations is optimized by the dispatch department in the Düsseldorf office. We are also active in the UK since 2003. We develop, own, and operate renewable power production facilities, and we are involved in the trading and origination of power from our own projects and also from projects of third parties. So traditional trading. Power plants are traditionally running either base load, the full day, or during peak hours for the 12 or 16 hours of higher demand. These are mainly coal plants, gas plants, and a smaller extent nuclear plants. And since the production is consistent and constant, selling power coming from traditional sources is straightforward. So the trader only needs to decide which products wants to trade and which combinations of products will bring us the higher profit. There is no risk, actually, of being imbalanced, so being short or long, as we call, unless there is an unexpected event that takes place, like a plant tripping. On the other hand, renewable energy is intermittent, and in other words, it cannot be turned on and off all the time, and the amount of power generated from renewable energy relies heavily on weather. In countries such as Germany, the power generated from renewables has priority dispatch on the transmission lines. It means that it takes precedence over electricity from more conventional sources. And as a result, any variations such as cloud coverage or wind speed can cause rapid swings in the power market. And many energy firms, like ours, have responded to this by shifting their trading activity into short-term products. So Statkraft in Germany generally has 60 gigawatts of renewable energy. So this is roughly equivalent to 60 nuclear power plants that can switch on or off, and it creates a huge need to know the potential wind or solar production. And from 2012, the German Renewable Energy Act allows for electricity to be sold directly via this so-called market premium model. And in order to motivate generators of renewable sources to operate their systems in a market-oriented manner, this so-called market premium is a financial bonus for the operators of all the systems of the generation of energy from renewable sources that move from this fixed EEG remuneration to direct marketing of the power to the power exchange. And accordingly, the UK market is based on the PPAs, the power purchase agreements. So the PPAs are usually benchmarked against the market index price, which is the average price at which each settlement period was traded. In general, the operations profit margin is set as a percentage of the market index price, which is around 90 to 99% of the market index price. So the profit of the trading companies is the remaining small percentage of this market index price. To give a number in this, with an average energy price during the year of around £40 per megawatt, this means that the whole profit margin per megawatt for an energy management team like ours is no more than £4 in the best case scenario. And when the actual production deviates from the forecast, the grid balances out by selling or buying from the counterparties that are short or long. So for this service, selling to counterparties that are short on a short system and long on a long system, the grid requires a premium, and this price are not on MIP levels. So again, to put a number of this on this, this spread could be up to £20 on peak. And taking that into account, also with the lower profit margins of the power generation, it's very obvious that any imbalances due to wind volatility can lead to big losses. Our trades for Germany take place between the day-ahead auction and the physical delivery. So our teams can trade the product day ahead, and the day-ahead auction in the German market ends at 12 o'clock of the previous day. The intraday market starts at 3 o'clock of the previous day, and the gate closure is at 3:30 of the current day. The physical delivery should start at 4 o'clock. So when we speak for short-term energy, for short-term forecast, we really mean hours ahead, so day ahead or really hours ahead. And accordingly, the UK market, the gate closure is 45 minutes before delivery. So generally, the whole forecasted volume of the day ahead forecast is sold in the day ahead market. And possible deviations of the day ahead market and the intraday forecast are traded in the intraday market. This means that wind is a price driver. And the wind profile may vary from zero production to full windy days with a production equal to the whole installed capacity. And this has a huge impact in the market dynamics and therefore in power prices. And from an overall system perspective, the grid publishes the forecasted demand for the following day. Energy producers then create expectations for the prices, and they schedule their plants to run or not accordingly. Thus, the market efficiency adjusts to the expected demand as a result, and as a result, supply meets demand at the price, which reflects the demand levels and the cost sourcing from the type of plants that are expected to ramp up. And of course, wind and solar forecasts are a huge part of this expected supply. And it becomes apparent that any fluctuations of the forecast can affect this supply-demand equilibrium and have a huge impact on the prices. And for example, if in UK the wind fails, let's say by 2 gigawatts, then demand will be higher than supply. All the buyers in the market will have to pay more in order to secure the power that they need for their clients. And with prices driving up, generators with higher production costs will be in the money, so they will also have to produce, and they will also put this amount of power in the market. So the market is efficient enough to adjust, but the forecast is the main driver in such a scenario that dictates the price movements and alterations in the generation mix. Here we have a small example of one of our offshore wind parks in the UK, where we got the forecast updates for the same period. The original forecast was at the 27 megawatts, and within 4 hours, we got down to 5. This was only one park. This happened to the whole UK, therefore all the prices went higher. Again, this is the same park, Sheringham Shoal, and these are the different updates of the forecast. We get updates every 15 minutes, and we have to take into account that some of the updates that we got were for periods that were already closed, so we couldn't trade these periods. We just could see that the wind was dropping. Now, from an individual company's portfolio perspective, the forecast is also the main driver. And based on that, the traders formulate a trading strategy. They analyze the market's renewable forecast and the portfolio forecast, and combining this with the prices of the market, they make decisions how to hedge their volumes and how to optimally dispatch their power. Of course, the forecast is likely to deviate, so the more precise a forecast, the more secure a trader will feel in order to take these decisions. So in the day-ahead auction, the traders base their decision on the day-ahead forecast, and it is usually price independent. So in other words, we sell the forecasted volume irrelevant to the price, or we try to. On the other hand, the intraday market is price dependent. When the day-ahead forecast is higher than the intraday forecast, then it leads to higher prices. When the day-ahead forecast is lower than the intraday forecast, then the prices are decreased. Here we can see the day-ahead forecast in red and the intraday forecast in green. If you notice the periods around 12 o'clock, can you see the numbers in the graph? There were prices going up to 140 euros. This was due to this difference in the forecast. Also here, the same event. Prices, the volume is decreasing, prices are going up. We buy forecasts from external providers. We also combine our forecasts. We create a meta forecast, more or less same as the previous presentations, to be honest. The quality of the forecast we get is generally good. The big problems for us are caused by extreme weather scenarios. And there are some days where the forecast can be extremely bad and we can lose a lot of money. And we try to optimize these days. So I have prepared some examples This one is from the windstorm Xava. It hit the northern Germany on Thursday morning, the 5th of December 2013. And its strength surpassed any expectations. So here we can see the European model performed 2 days ago, and it was valid for Thursday, the 5th of December. And it expected wind speed higher than it was actually produced. So here we can see our production for our company, our portfolio. And the initial forecast was expected to be around 7 gigawatts. And when we got the settlement data, it was around 5. So 2 scenarios could happen here from a trading point of view. In the best case scenario, the traded volume is lower than the forecasted volume. So let's assume, like here it was, the day ahead forecast would be 7 gigawatts, and a trader chooses to sell only 5 gigawatts in the day ahead auction. And then we are left with 2 gigawatts to be traded in the intraday market. So let's assume that the following day the actual production is 5.5 gigawatts. Then our position would be 500 megawatts long. But the whole Germany is short, as everyone had the same information. And everybody thought that the production would be 7 gigawatts. So the intraday prices are higher than the day-ahead prices, and we are able to sell this difference of 500 megawatts and make a profit. On the other hand, again, the day-ahead forecast would be 7 gigawatts, but the trader, having faith in the forecast, trades the whole volume day ahead. The following day, the production is again 5.5 gigawatts, and our position is then 1.5 gigawatts short, and the trader has to buy this volume at a very high price. This is another example of the 25th Christmas of 2015. The day-ahead forecast is the dotted line. The intraday forecast is the green line. So we traded the forecast day ahead. The next day came. Prices were very low. And the bad thing is that everybody had this information. So the first graph was our forecast. The second graph is the forecast of the whole Germany. So everybody had this information. We couldn't do anything. We lost a lot of money. And here is the prices for this day. The green cells are the prices, are the timestamps where the intraday price was lower than spot prices. So, and this is also the evolution of the prices day by day for the same day. So we can see that it was red in the beginning, and when the time was coming, it was becoming greener and greener. And this is an example of the EEG solar. It's from the solar eclipse that was mentioned before. This is the forecast for the whole country. So we had a drop of 7 gigawatts, I think, and then up for 14, an increase of 14 gigawatts. The day ahead forecast, the day ahead price, sorry, was deviating from 400 euros per megawatt hour up to minus 164, which are extreme prices for the day ahead. I think that we've never seen prices like that. And this was due to everybody getting a forecast like this. Everybody was having no faith in the forecast. They tried to balance their position. They tried to smooth their profile. And this led to crazy prices day ahead. But even funnier intraday prices came. So the same quarter, 9 o'clock, the last quarter, so 45, it took prices for 100 to minus 974. So people were paying 1,000 euros to sell their power. So it was for the same quarter. These prices, the high and low, is for the same quarter. So it's extremely crazy how much the trade was deviating. People had no faith in the forecast. They were doing really things that were not predicted, and yeah, that led to a lot of losses for trading companies. And I think that should be it. Yes. Thank you.
Thank you very much. I take the privilege of being the one with the microphone to ask the first question. You're saying, you're talking a lot about faith in the forecast, but you didn't really talk about probabilistic forecasts.
Yes, because we don't create our own forecast per se. So we buy forecasts from external providers. We benchmark their forecast, of course, so we pick a number of limited providers, having the best root mean square error and mean absolute error for day ahead and intraday forecast, last tradable actually, and we create then a meta forecast on our own, combining these forecasts. But I think this is mostly what trading companies do. Mostly we don't create our own forecast, so we have faith that there are companies that are exclusively working on forecasting, and our job is to benchmark and find them, then buy a forecast from them, and on our own we try to combine these forecasts. So we don't take weather models, we don't create a forecast on our own.
But these forecast providers will be happy to provide you with probabilistic forecasts, with a distribution of forecasts.
Yes, we have quantiles. That's, of course, I could also bring examples where the forecast is out of the quantiles also. So even the day-ahead forecast can be different by a huge number from the Q90 or Q10. So we've seen also this. We see this also every day. But it's extreme weather scenarios that concern us more than the day-ahead operation, where we can, of course, if the prices are normal, we can balance this in the market. But the extreme days with prices at minus 1,000 euros, these are the ones that cause us a big pain. And these are also the spots that we would like to avoid, having a bad forecast in such days, while the other days are better to manage, actually.
I have the microphone too. This was actually also my question or comment, because we have heard from Helmut earlier today that asked where should the uncertainty forecast be used. I think it's exactly in the extreme events where uncertainty forecast from Ensemble, for example, is what would help the market to actually understand errors or the expected error that comes much earlier than beforehand. It's the only technology where you can actually predict the expected error, and in that way trade your imbalance already many hours before, because it's to avoid that if everybody waits until 2 hours before, this is where the negative prices come.
Okay, so in this example, the whole Germany, all trading houses in Germany had the same information for the day-ahead forecast. And we had, our quantiles were having such a big difference. This is, I think, an example that the day-ahead forecast had such a huge band that we couldn't trust it. No trading house could trust the forecast. Therefore, the difference for the intraday, for the day-ahead prices were at 500 euros day ahead, while usually it should be around 40. So, yes, I mean, they all saw this. We all knew, we didn't know what to expect, actually, day ahead and intraday. And they went, should I say, completely crazy. They didn't know what to do. They were buying, they were selling.
But that's exactly it.
Yes,
it's because nobody knew what to do.
Exactly.
And that's why I think it's important that the market starts understanding when we can trust in forecasts and what means and tools are there available to also make a prediction of what to be expected. Then these situations will no longer happen. I'm sure.
I agree that there should be education on the trading side, and they should have better understanding. It's on the other hand, since I'm working with traders, I also understand their frustration and their fear when they have to buy or sell a product and they see a forecast with quantiles deviating so much, and they ask me, is this true? Can I trust it? I mean, I also tell them yes, but I hope that they don't lose money. And there should be a better understanding from the traders on the forecast and what the forecast actually means. And this is very, very helpful for us that we get from our suppliers. We also get updates. We get also phone calls explaining why the forecast will be behaving this way due to a reason that we may not know by just buying a power forecast, so power production forecast. Yes.
Based on this experience and the reaction of the traders and the market, I would be really more interested to know what could be your recommendations to adapt the market rules for renewables and for these situations that are not predictable, rather than the recommendations what we have to do to improve predictions, because we know that this is difficult. And I think one of the big questions is what market structures are best for the future for high penetration from renewables that we are going to have even higher in the next years, decades. So maybe this can be discussed at the end.
Yes, I think.
I mean, should we improve the input, which is the forecast, or should we improve the tool that use the forecast and has big consequences, which is the market rules that should be adapted more to the renewables?
Yeah, no, I understand. I think you're absolutely right. We should find ways to adapt all this renewable penetration and make it more smooth and more predicted. I don't know if I'm the responsible person to make recommendations, since I only work with forecasts, and I only speak with providers, not with the market actually. So, but there is room definitely for improvement. I think the TSOs, the power generators should all sit down. The forecasters should sit down and talk and decide.
From ensemble providers, when you get the data, do you have a standard of what should be the ensemble size, or you just don't ask for the ensembles themselves? Do you ask for the ensembles?
I couldn't hear you very well.
Do you ask for the ensembles, and when you ask it?
No. There are parts of our company that they get ensembles. They get forecast for some days ahead, and I know that they use ensembles. We, in these trading teams, the intraday trading teams, we only use power production forecasts with their quantiles, of course. But we don't use ensembles.
Yeah, there can be ensembles for power production also.
Excuse me?
There can be ensembles for power production also.
But do you mean quantiles, or am I?
Yeah, you can get quantiles from ensembles, but...
Yes, okay. Then, yes, the quantiles we get are also product of ensembles. So, but we only get one figure at the end.
Okay.
Okay, if I understood correctly, you have some kind of dependency between the price forecast error and the wind power forecast error. So, did you consider to model this dependency? Because it's, if you do that, you have some more information.
We do. We have considered this. We tried in the past. But in the beginning, I said that our company has has around 9 gigawatts of wind in our portfolio. And there are 30 in the whole Germany, 35. So when we try to change that based on the price, we also affect the price. So it's a vicious circle, and we cannot do this actually.
Okay. So it could be interesting also to
yes,
predict the curves of the competitors and how they change according to...
Yes.
No, there is a lot of things that from the, let's say, research point of view can be done to improve.
Yes, definitely. There are many things. We don't claim that we follow the best path. The bad thing about us is that our portfolio is so big in Germany that whatever changes we make, we affect the prices. And we cannot predict anything with this. So.
It is possible. It is possible.
Maybe.
I think we have to close it here for time reasons. There was one question from the remote audience that I think was interesting. That is, how do you actually identify difficult situations? I mean, you're saying the biggest pain for you is difficult days, and how do you know them in advance?
In advance, sometimes we get, as I told you, heads up messages from our provider, so we know that the day is coming. We don't know exactly what to expect, or we have this uncertainty. This also reflects on the prices. And yeah, this is how we know how to anticipate it. Sometimes we can take actions because we can down-regulate parks. Sometimes it's impossible, like this solar example.
Okay.
Yeah.
Thank you very much.
Thank you.
And then we get to the last speaker of the morning session, Sophie Guignard. She is part of a team at a operator and developer of wind farms. So that's yet another view.
Thanks. It's the first time I present my work in English, which is not my native language, so I'm a little bit nervous. I'm sorry if I make some mistake, but I'm gonna try. My name is Sophie Guignard, and I'm working for Mayaolis, a French wind power producer. And today I'm gonna talk about forecast, and more precisely about their use in our company. So, to begin, a small presentation of Mayaolis, because I'm not sure everyone knows this company. So Mayaolis is a branch of ENGIE, the global energy player, and in fact, since a few days, they became our main and only shareholder. And I put some figure about the company. For example, our first wind farm was commissioned in 2005. We are 18. And our headquarters are in Lille, but we also have office in Lyon and Nantes, and we have 3 maintenance centers. About our skill, one of the specificities of our firm is to manage every step of wind farm project. So we have various departments for that: development, from site research to administrative approval, construction for building phase, operation for monitoring. And we don't use a manufacturer for the maintenance. We have a department dedicated to it. And for example, we repair blades, and it's important for the next. And we also have expertise for technical support and research, and that's my department. So, after this more introduction, let's focus on the subject of the day, forecast. And I'm going to start with a small story. And in 2007, we started a benchmark in order to find a forecast provider. So, about 20 companies was contacted and 10 were tested. And after that, in 2008, we established a supply forecast with the first provider. At this time, we had only 10 wind farms, and the forecasts are delivered each 15 minutes with an horizon of 6 days, and the normalism and absolute error between 6 and 26, with an average on 12 for the first 48 hours. So after that, in 2012, we decided to develop our internal model, and to do that, we used weather research and forecasting model. So we have forecast each 10 minutes with a deadline on 8 days, but the normalised mean absolute error is not really good. It's between 4 in the base case, but in the worst case, it could be 45. So it's a very big mistake for us. So now we are in 2050. If you're an addict of TV shows just like me, maybe you recognize Barry Stinson from I Met Your Mother, and one of his famous quotes, "New is always better." That's why in this year we decided to try to organize a new benchmark, and we hope we have a better result. And it was just a small one because we only test 4 providers, And after that, we chose one of them. And now we have 10 zones, but we have 22 wind farms. We regroup some wind farms in order to have an aggregation. And now forecast is each hour, and we have a deadline of 10 days. Actually, what is our current of use for forecast? We use them for maintenance, managing budget, and also for research and development project for grid integration. So, after almost 10 years, what do you learn? Maintenance and efficient model can be very costly. We realize it when we try to create our own model. It costs workforce and computing power research, and that's why we don't use it actually, because we can't maintain this model. It's very difficult for our small company. Another point, some wind farms are hard to predict. Regardless of the provider, we find that some wind farms have always a better result from the other. I put a table to illustrate. We have 2 wind farms and 3 providers, and as you can see, it's always the same wind farm we have the best result. We suppose it's because of the field, but we are not sure of that. We don't study this case, so it's just a supposition. And another point on our feedback is an interface is very important for our use. Why? Because our users are not engineering or not a meteorologist. They can't interpret data. They just need to read the forecast and to understand what's going to be happen. Now I would like to present an example of error. So it's a bad forecast, and it's a recent one because it took place a few days ago. It's Friday. It's on a Friday, 27th May, and this is the forecast for all our turbines. What can we say? It's May, so it's not a good month for production in France, but okay, it's possible. If we focus on the wind for a turbine on the north, we expected a wind at 6 meters per second for the Monday, the 30th. So, if we want to repair blades, it's possible. It's because the wind is not too high, so we can repair blade if we want. Now this is a new forecast, the forecast of the Monday, and we thought on Friday we only produce within 1 giga, and it became a forecast almost 3 giga. And if we focus on the wind, now we have a peak at 10 meters per second, so we can't repair blades. It's too dangerous. And our technician can work. So it's very difficult for the maintenance planner. He had to find a solution. What can they do? Because they can't go to repair the blade. So what's happened? Honestly, I'm not sure. It's recent, and I don't have time to study the case. I only have an assumption, maybe gusty winds or an unexpected. I don't really know. I don't know if you have some solution. And I can present other type of errors. Sorry, it's in French. I don't have time to change the illustrate, the picture. I speak about base error, and we also have phase error when we we think we're gonna be wind on the morning, and in fact, wind comes at the afternoon, for example. So, after 10 years, we have some wishes for the forecast. What is very important for our is a good interface, because as I said, we need something simple, because they are not engineering which are read the forecast, so they need to understand what they can read. If we can, it could be a good thing to have more precise forecast and at least a better indicator of uncertainty. And so to conclude this presentation, I can speak about future and what we want and when we try to develop. It's important, I think, to develop advanced forecasting model, and in the future use, product consumption forecasting, for example. And to finish, I just can tell a few words about a project research for EWA. My EOLIS is involved in this project in association with ERTA and EDF and the Research Lab. And the goal is to modeling, forecasting, and risk evaluation of wind power production, and to focus on risk. So, thank you, and I can try.
Thank you very much.
I hope you agree.
Thank you. When you do blade repairs, and certainly when you do many other operations during construction and maintenance that involves any kind of lifting of equipment, it's you mentioned gusty winds. It's not just the mean wind speed that really matters. It's maybe the max speed, the gust speed. I mean, is that something you have looked at in your benchmarks, specialized forecasts for gusts or maximum wind speeds?
Yes. Yes, we need this because our use is for maintenance. So for maintenance, they use this information. So yes, it's important for us. It's one of the points of the benchmark.
So what's your conclusion on the accuracy of this versus a comment on the accuracy of the gust prediction forecast versus just the wind speed forecast?
I think we could improve this point.
Yeah.
I would like it. It's possible too.
Thank you for your presentation. It was clear. I was wondering if you have ever evaluated the benefits of having forecasts in terms of maintenance, and especially preventive maintenance.
Yes, we start to use it, but honestly, it's very complicated because we don't have many work. It's a big work, and we don't have the resource. But we're gonna try to understand what it's happened and it's a good thing or not to use that.
Well, if that's all, then thank you again. The next point on the program is not lunch. It's group picture, but then lunch. So if you could assemble somehow out there for a group picture.
Is this room going to be locked?
Yes, it will be. So don't stay here. just go on. Yeah, you can leave the things, everything will be locked. The way to the lunch, just if we disperse after the photo, is instead of going out, you go to the left at the end of the corridor, and you will see a kind of lake. We are having lunch by the lake. Okay.
Well, we'll assemble here at 2 o'clock again. ag, but mostly from forecasters. So we are going to have some presentations from the forecasting world, and then as the last one, there should be some discussion on what we've learned today and what we think are the issues that we should be looking at. But now for the first one, once the two gentlemen have fixed their presentation.
It's a trap.
We're going to hear from Stanislas Dublot and Aurélien
Ben
Daoud from Compagnie Nationale du Rhône, who were, to my knowledge, some of the first ones to actually have meteorologists in their own forecasting team.
Exactly. Thank you for the introduction. Thank you for the organization. I'd like to say hello as well to the people who are not here, but who are following us. I don't know where are the cameras, but they should see us and hear us. I'm gonna try to make the best out of this after lunch presentation. It's not easy. We could have spoken this morning actually in the end user session, because we are end user, but as we are involved in meteorology since a long time, we put the focus of this presentation on the meteorological part as well. We'll start with some background information about our company. We'll tell you how we do forecast, and we lay the stress on one specific case. We won't bring a lot compared to state of the art, but we thought it was interesting to speak a little bit on a French case. I haven't seen much talk about French cases. Well, we had one already this morning, so maybe things are changing. It's good for us. CNR is Compagnie Nationale du Rhône. This is France's first only renewable electricity producer. So it's a way of not saying that we are the second producer in France, far behind the big one, but still second. And we are half public, half private, and the private part is owned by ENGIE Group, like Mayaolis this morning. Historically, we do manage 19 dams in the southeast of France on the Rhône River, and since 2006 we developed and bought wind farms. Now we have a little bit more than 30 wind farms for 380 megawatts, and we do own as well photovoltaic farms. Our wind farms are quite well located in forecasting point of view, because we have many different meteorological situations, and that quite smooth our forecasting error in the total wind farms level. As I said, historically we forecast rain and flow for the use of the optimization of our hydroelectric production. We have run-of-the-river dams. Run-of-the-river dams are dams without big storage, so we need to be very precise in terms of rain forecasting and to work very closely with our front office, the optimization team, the remote control team. So all those guys are in the same open space and work together. So it was a really good start for working on intermittent power production forecasting. That's what we do since 2008 because we wanted to optimize the maintenance of our parks.
In 2008, it's not written here, but the prices on the market were really high and much higher than the feed-in tariffs. It has to be said here that in France, you still have feed-in tariffs for wind parks production and PV parks production. But it is changing. Like for small hydro, for example, it has changed the last 2 years. It is said that it's gonna change for wind power as well in the 2 following years. We don't know exactly. The law is not written, but that's gonna change, and we want to be ready for it. And there is several other objectives, but I will speak more about our forecasting system now. CNR know-how applied to wind and solar power forecasting is embedded in a tool called Apogee. Apogee has been in-house developed because we wanted it to be integrated in our IT system, which is quite specific. We manage different spatial scale, temporal scale. It provides deterministic forecast and associated uncertainties. It's quite simple in terms of probabilistic forecasting because we don't use much probabilistic forecasting so far. And one of the main features of Apogee is that it leaves room for meteorological expertise. That's what Aurélien is going to talk about next. The current operational use, we have about 9 wind farms for which we provide forecast. It's mainly for training because, as I said, we have feed-in tariff. We do provide forecast to our maintenance team, so it helps for maintenance. But the main goal is to train, and especially to train for other third-part parks for which we provide forecast as well in the NG group, or for a company called GP Joule. They were looking after a company who has good relation with the French TSO. So it was more man-to-man contact that we have with them. And we do provide forecast for small hydro from private owners because, as I said, there's no feed-in tariff anymore for this kind of small hydro. Consequently, they need forecast. And they need a relation to the French TSO. And we do benchmarks as well because it's really interesting to improve our own forecast. A little bit more of methodology. As I said, we don't have a lot compared to state of the art, but it was important to describe a little bit more. You guys know IFS and GFS models. We work a lot with Meteor France, of course. So we use Arome and Arpège. We've been using Arome like for a year only, but it's quite interesting because the resolution is 1.3 kilometers. It brings quite a lot of improvement compared to Arpège, let's say, which is the global Meteor France model. And we've been tested Cosmo, the Meteo Suisse model, for 6 months now. Everything in a multimodal approach. We use, of course, also on-site observed SCADA data, and like we said this morning, we have some problems about the quality as well, and we use some farm availability data, at least the one we can plan. The modelization the modelization strategy is based on what's in the state of the art. Neural network, ARIMA model, model output as statistics. As I said, the probabilistic part is quite simple. The two specificity maybe are the fact that we keep some simple model and we keep a two phases modelization strategy, win and local win and then production, because we want to keep an eye and a hand on the win forecast. Aurélien will talk a little bit about more of this. We want to be able to add some human knowledge to the forecast. And the last results is the results of a trial. So we were happy to be in this trial. We were tying for the first place. So that was quite a satisfactory result. We are not better than others, but at least we are in line with the state of the art. Some shots from the Apogee interface. Here you can see a list of the NWP's inputs. There's a graph with the local wind speed forecast, the wind farm production, and what I said in red, the meteorologists can modulate the red curve according to their expertise. Here we can see a shot with availability data. You can enter availability data. That's interesting because the first software is a quite old software used in hydroelectricity purpose at the beginning, and we adapted it. And the last one is our online web interface for the third part who are using Apogee and for our exploitation team on site as well. Now I leave the stage to Aurélien, our meteorologist.
Thank you. So I will give some words about meteorological feedback. I will just focus on one case study. At the beginning I wanted to study two cases, but I didn't have enough time, sorry. So the event occurred in February 2016, so this year. It was recent. Here you can see the observations and of the mean sea level pressure over France, and you can see the low level pressure system that is coming from the Manche Sea. So here it is at 6 UTC, and 6 hours later the low pressure is near the Cotentin region in France, with high wind speeds south of the system. And 6 hours later, the low pressure was centered over the Parisian region, and here you can see that the gradient, the pressure gradient, is very strong. So you can have very variable wind speed in this area. And finally, 6 hours later, the low pressure system moved into Germany. So this is a particular case because the low pressure system is very small, quite small if we compare to usual low pressure systems. Here we wanted to produce forecasts for day-ahead market. So we made the forecast the day before and before 12 CET. And wind and temperature forecasts that the input to the algorithm are based on the NWPs running at 0 UTC. And for the expertise, we use expert charts from different NWPs available over France. So Stanislas talked about it a little bit. And we use additional models such as the UKMO or the GEM just for the expertise to see the differences between the models and to see in some words, to make an ensemble prediction based on different models. So here the lead time is at plus 24 hours. Here I just show you some maps from the different models, only 4 models. So the GFS here, you can see that the low pressure system is well forecasted and is coming from the Atlantic Ocean. And the other models were very close to GFS for this lead time. So as a forecaster, you can think that the situation is not so uncertain for plus 24 hours. But if you look at, so here the GFS, Arpège, ECMWF model, and the GEM, so they are very close. And if you look at 24 hours later, so for a lead time plus 48 hours, you can see that the GFS model places the low pressure system over Germany, but the Arpège model, for example, the low pressure system is over northern France. Whereas the other models, the ECMWF model and the GEM, the low pressure system is also in Germany. So here you can think that Arpège is an outlier model. So here we can summarize as at plus 24 hours the NWPs are very close with small pattern differences, and 24 hours later the NWPs are not in agreement with Arpège as an outlier. The other models suggesting a similar tracking of the low pressure system. And finally, the expertise, given that CNR wind farms, for CNR wind farms, only Arpège, AROM, and ECMWF model are used for day-ahead market forecast as input to the algorithms. A more important weight is applied to the ECMWF forecast, especially in northern France, given that Arpège and AROM, which is a limited area model based on Arpège pattern, we finally choose the ECMWF model. So concerning the multimodal approach in Apogee, here on the following graph, F1 Arpège corresponds to a statistical adaptation from Arpège model. The CEP corresponds to the ECMWF, and the F1MM corresponds to the multimodal algorithm, that is a statistical adaptation from a combination of both models. So, and this algorithm is for us kind of reference because it is the best algorithm in average. And in addition, you will see the expertise on the graph. So the expert corresponds to the forecast based on expertise. So here is just an example of Menia wind farm in northern France. So this is located there on the maps. Here you can see the graph of the wind speed forecast. The observed wind speed is in blue, and the F1 Arpège is in one kind of green, and the other green is F1 CEP, so the ECMWF model. And the multimodal algorithm, that is the best in average, is in the other green color, and the expertise is the gray curve. You can see the difference at the end of the period. So up to 38 hours, we didn't expertise the forecast because the uncertainties were quite low. But later, you can see that the forecast with expertise is more based on F1 CEP, because we choose the ESAM-WF model as the reference model for the forecast. So we gave a higher rate to this source. So you can see here the difference between the curves. And then in production forecasts, the result is the following. Here you can see that there is a high deviation in terms of production between the observation and the reference algorithm, the multimodal F1MM, whereas the expertise is closer to the observation with a well-reduced error. Just a few figures. The cumulated production over 24 hours this day was 39 megawatt hours. The error level, here is another score compared to this morning. This is the sum of the hourly absolute errors that they had. And this error is very low for the experts, 30 megawatt hours, whereas for the reference algorithm, it was much higher, 45 megawatt hours, so 30%, a reduction of 30%. So in conclusion here, the meteorological expertise is applied when uncertainties are high, so it's not so frequent. Uncertainties, especially when different low pressure systems trajectories are observed, or temporarily when there are ramps. For example, we have just a look on the forecast to check if expertise is needed or not. This expertise is also applied on one signal, but also on several wind farms located in one region under the same meteorological influence. So this is important for us. This expertise is applied by weighting different NWPs, allowing an expertise at a larger scale. That's what we want to do in the future. This is only the choice of one or several models, so that is giving different weights to the models at a larger scale, instead of just modulating the wind speed curve as we saw just for one farm. And it's important to keep in mind that at CNR, wind and solar energy forecasting is built on the meteorological experience acquired with its historical hydro activities. If we had never had this meteorological experience at CNR, I think we wouldn't do this kind of expertise for renewables energies. Also, our other mission is to communicate forecasts to our exploitation team. So here is just a picture showing the CNR forecasting report. On this report, you can see, so this is a report made by a human. So here you can see on one row the qualitative wind speed forecast. So the production will be low, very low, medium, or high for 7 days ahead. We have also meteorological analysis for the exploitation team. To help them to understand the forecast, and they have also qualitative lightning risk forecasts and qualitative high wind speed forecasts in order to manage their So that's the reports that we do every day in the week. And I will just let Stanislas to conclude.
For the conclusion, very quickly, even if we are young in the field, we've noticed since 2008 that the NWPs have improved. And maybe more than further improvement, if we can dress a wish list, it could be worth working on very practical and maybe easy issues, like providing hourly forecasts. I don't know about you guys, but we don't get hourly forecast for the IFS model because we have to go through Météo France, and Météo France, they don't provide hourly forecast of the IFS model. It's just 3 hourly forecast. So we have some gaps, especially for really short-term forecast. As we said this morning, I don't remember who, but it would be interesting to shorten the supplying period after each run. With Arome, we've got 3 hourly updates, so that's quite an improvement compared to IFS, for example. And the issue of providing reforecasts when you've got a big update, like we had with IFS in March, I think, it would be interesting to get the reforecast for our statistical model, to recalibrate our statistical model. I think it's available for ECMWF, but I didn't manage to get them. For Météo France model, it's not possible, for example. We've noticed that we haven't seen any improvement using more than 3 good NWP sources, and as Aurélien said, human expertise bring improvement in average, but it has to be facilitated. Like you saw that in the red curve, you can adjust the forecast for one wind farm. It was kind of a 2008 development when we had only 8 wind farms. Now that we have 35, we have to think about another way of bringing human added value. On our side, ongoing development are short-term wind power forecasting. Like this morning, I think it was Ricardo asking about like the spatial temporal nowcasting based on SCADA data. We could do this with our 35, or at least we could try. We are trying with George on PV, with our PV farms right now. We have to do more for monitoring and assessing the plus brought by the human expertise. We are looking at ensemble forecasting because we do kind of quantize forecasting, but we don't really use them. Ensemble forecasting could be useful with the last point because we have a quite big project willing to combine hydro, big hydro and small hydro, PV and wind energy production management together. And we would need uncertainties forecasting, probabilistic forecasting for big hydro, small hydro, PV, wind, and that's one of the big projects that's going on in our company. And maybe I just received a text with the last forecast here saying that the French football team is gonna win the Euro 2016. So, thank you.
Well, I'm sure both our Spanish hosts and the Germans in the room would like to see the uncertainty bands on that.
Yeah. We don't use uncertainties so far. So
we don't like it in French.
Okay. Questions? While Pep is searching for the microphone. Because if we don't, we don't have that much time anyway, then that would be fine too if we just continue.
He's coming.
Just a comment. Reforecasting is really expensive. So if you want to pay for it.
Oh, yeah.
Yeah, to reforecast, I mean, and usually when an operational centre, they do a lot of testing, but it's not usually a reforecast because there'll be changes while they're doing it. So it's as bad as the change. You're probably better developing adaptive statistical methods than trying to get reforecasts, I think.
Yeah, it would be only like once every 4 years or 5 years when there's this big update of the. Yeah, expensive for the Met Office, for example. Yeah. But I think they do that at the ECMWA. They provide reforecast.
The Americans do that usually, but it's maybe a week or 2 or 3 max.
Yeah,
because people adjust all their processes and stuff if there is changes, but yes, it's too expensive.
ECM doesn't have an e-suite.
Okay. Thank you very much. The next speaker is Stefan Vogt from the Fraunhofer IWIS, and he's going to talk about nodal forecasting.
So, hello everyone, thank you for this chance to give this presentation. Yeah, I'm Stefan Vogt, as you already heard. I won't tell you so much about Fraunhofer IWIS. If you have questions, maybe you come afterwards to me and we can talk about. So, a little bit into the agenda, I have a comparison of 3 methods which are very simple, basically to forecast power plants where you don't have any power measurements. And I will present you these 3 methods, and afterwards I show you some results on a little experiment I made. And yeah, then I come to conclusions. So, as an introduction, grid node forecasting is a topic which is somehow connected to the topic from Meli. We have the problem of differences in the power feed. A way to do grid node forecasting, a simple way to do so is just to take the control zone forecast and just divide it by the installed capacity of the grid node areas, and so it's mainly proportional to the regional, or it's proportional to the regional forecast and the installed capacity of a single grid node. So the installed capacity of a single grid node means in an electricity grid, you have some power plants connected to one of this grid node, and it can be seen as kind of a region where those plants are standing, and in this region there is a certain amount of wind power. As we have already seen, also the problems are somehow rising with rising or increase in wind energy, and what you could for example, see is that there is an increase in redispatch. The data you see in the left corner, this is from netztransparenz.de, which is a page where data is published from the TSOs, and they also publish the cases when there is a redispatch measure and how much power they asked to rise, or to the negative way, the negative redispatch. And so actually it should be 0, the sum of both the positive and negative demand, but since a redispatch is usually defined as I have a problem in my grid, there is like a bottleneck, and therefore I have to turn one power plant on, whereas I turn another off. And if you look at this data, there is like a bias. This is the yellow curve. This is the sum of the blue and the red, so the sum of the positive redispatch demand and the negative. And this is not zero. Well, I'm not an electricity grid expert, actually, but I think one reason for this is that there are wind power farms producing energy, and I'm not 100% sure about this, but for me it looks like one reason for this is also that there are errors in forecast, and that the errors in forecast are spatially varying, that there are, for the assumption of some grid node forecast, or for the feed of in a grid node, that there is sometimes more or less. So to improve this, or to reduce the redispatch measures, it's maybe a good idea to make refined forecasts at grid nodes, which are better than just dividing it by the installed capacity. And therefore, in Germany, as we learned today already, we have a lack of online or real-time measured power wind power farms. And so we have to do a lot of assumptions for wind power farms which are not measured. So one way to forecast it, it's very simple here, and maybe it's also related to what we heard in the morning. It's just more or less interpolation of the normalized power of wind farms at a certain location of an unmeasured wind farm, and afterwards you take the capacity for this plant and just multiply it again. So in this graph it's a little bit complicated. On the left side you see the input in the models. The models, which are called RWF, standing for Reference Wind Farm, they have the input of the NWP forecast at this location, for example, wind speed, pressure, and so on. And also there is the last, in my example, I took the last 12 online real-time measurements in a 15-minute time resolution. And instead of neural network, I tried something new called, or it's actually not new, I tried something else called extreme learning machines, which are basically neural networks with another way of training it. And I made one of these regression machines for every forecast horizon, and I did 32 forecast horizons between 15 minutes to 8 hours in the future. So you have short-term forecasts for with these extreme learning machines at every reference wind farm location. At every location you have real-time measurements. And then in the next step you just interpolate this, or actually it's not interpolation, since it's more like a regression. We have kind of a kernel interpolation, kernel regression. It's if you know, maybe it's called Nadaraya-Watson regression, and this is used to estimate this. It's very similar to inverse distance learning, but that's over the top. Maybe just to explain it a little bit better, on the right side, in the on the right edge down there, you can see two wind farms, wind farm A and wind farm B, where you have some forecast, and another wind farm C where you don't have a forecast. And the way you build up the forecast for wind farm C is you make a linear combination of the forecast of the both others, and to find the linear weights you just have this radial basis functions, and a proportion to each other gives you the weights for this wind farm C linear combination, where you don't have any measurements. Another way to look at, or to forecast farms where you know nothing, is to take a generic power curve. For this case I used a generic power curve from the Trade Wind project, which works very well. Actually introduced 4 or even more for future cases power curves, but I just used one since this is working with a lot of plants very well, surprisingly well, although it's a very simplification of a physical model. And what you do is you take the nearest NWP grid point, look for the wind speed and hub height, put it inside this power curve, and you get a value. And you can do it for every wind farm and see what happens. What's bad about it, there are no real-time measurements included. And therefore I present method 3, which is kind of a combination of those both methods. You have again this radial basis functions, which gives you the weights for wind farm A and wind farm B down in the right corner. But next to it, there is a weight for the power curve. And to estimate this power curve weight, you have this constant deep purple line down in the right corner over the green surface, which just means to be some surface of the Earth. And this weight is more, it looks like it's constant, but if you set it in a proportion to the radial basis functions, you see that if you are close to a wind farm, then the weight, or a reference wind farm with measurements, then the weight for this reference wind farm is higher than this constant power curve band. Oh, sorry. And but if you are far away of any reference farm, then the radial basis functions has very low values, and therefore the power curve is the only one mixing in. So this was the idea. I am far away from somewhere, then I want to, from any measurement, then I just want to rely on a power curve. If I'm close to some reference farms, then I want to take them more into account. The experiment I made is just for about 2.5 years of data. I split it into train, validation, and test, since I had to find some hyperparameters, and I did this on the validation set. As I already told, I used the 12 previous 15-minute real-time measurements of altogether 58 wind farms, which we actually have online, and but it's not SCADA, it's just really power measurements. And this is done every 15 minutes. And then I use this data plus the numerical weather forecast, the youngest I can have at this point of time. So for us, IFS is 6 hours and 15 minutes old. So the model run started this time earlier. And we can use this data together with the last measurements and just put it in our reference farm models in method 1. And on the same time, we just take the same data from the NWP with the wind speed and hub height into our power curve for the second model. And the third model is the combination with spatial weights. I forgot to write that it's method 3, but you see. And then finally we have 82 wind farms measurements, but not all of them are really online real-time measurements. So the set is bigger than the set of real-time measurement wind farms which go into the algorithm. And to validate, I used the leave one out method, where I just took one of those 82 wind farms out, or let's say one of those 58 wind farms out, and then I did this algorithm and looked how good is it on this specific wind farm, and I repeated it for all the wind farms. And so I got some results for the over the forecast horizon, and I just calculated the average of all these results to get an idea of how the algorithm is generally working. And this is what you can see on the right side in the graph. And you see there is the forecast horizon on the x-axis between 15 minutes and 8 hours. And you see the RMSE between something like 11.5 and 12.5. And the lines are the actual average. And then also you can see like a color band next to these lines. So every line is standing for a method. Just to repeat, method 1 is the reference farm method, method 2 this generic power curve, and method 3 was this combination. And every line stands for the average. But there's also this color band, and this is like a bootstrap of those. So I made an average of 82 error values, and I took bootstrap samples out of this 82 error values, and I repeated it 1,000 times and got an distribution. And what you see is the interquartile range of this bootstrap distribution. This gives you an idea of the significance of the improvement, if this is really reliable for any. I speed up a little. And you see here, actually there are overlapping ranges, which is bad since this is then not clearly significant. But if you look at the differences of the NRMSE values between the methods, so I just compared method 1 to method 3 and method 2 to method 3, or the other way around actually, and you see all are positive. So there is every time an improvement. Only for the reference farm within the first half hour, the significance level of 1% was not totally reached. But in general, it's clearly significant of this set of wind farms. So I come to the conclusions. I've presented 3 methods to make forecasts for wind farms you don't know, which is necessary for grid node forecasting. And I did a little experiment on 2.5 years of data with 15 minutes power measurements, which showed that the combination is actually working very well. On the other hand, the generic power curve is doing surprisingly good without real training or something. Yeah. So if you have any questions, I would like to answer them really. Thank you.
So I was wondering if the problems you mentioned in the second slide was not because you are not considering the network topology, the electrical network topology.
You mean
these problems? Yeah, these ones.
Yeah. So it's yeah. Actually, I took it as a motivation. There is a rise in redispatch measures in the last years, and this appears especially during wintertime when there is more wind power feed-in. Okay. And therefore there was kind of the suspicion that this is connected. And
we have a real demo in Portugal between the DSO and the TSO where we are providing this kind of forecast for the nodes of active and active power, but from the DSO side. So they have all the information and even the network topology. So what we do is that we forecast for each nodes on secondary substations, medium, low voltage substations, and then the power flow, you run the power flow with electrical equations, it calculates you these values in the transmission nodes. So if they change the topology, you don't have an error. In your case, you might have if they transfer some of the generation to another node, so you have more generation on that node and less in another one. Yeah. And the problem is not on your model, is let's say they are mixing the nodes.
One problem I assume to exist is that if you just split your regional forecast for the whole control zone up to the capacity of all grid nodes, then maybe you are making major errors, since maybe there is a high power production in the north and not in the south, and therefore there is a difference, although a difference next to this capacity.
I know that changing the topology is quite common. They do this several times. So this could be, let's say, a variable that you are not taking into account, and this might give these results, but I'm not sure.
Actually, we get monthly information on the grid node connections, and we just take this into account that the capacity is calculated again with the information of the connection to the grid.
Okay, but I mean from 1 hour to another. So in 1 hour they can change. So you miss that. That is probably the reason. I don't know. It's okay, just one comment.
Thank you. Okay. We have to stop the questions here now. And I'd like to welcome my next speaker, who's Gil. Who's, put it here somewhere.
Where? This
one. Yes. Thanks. And he's going to have a little bit of an outlook on seasonal forecasting.
Well, that was the original idea. But, but when I received your email, I have the feeling that probably this is not the forum to try to convince you that there is the seasonal forecast technology over there. So I try to provide more reflections and thoughts from people who we are doing the forecast for the wind industry, and try to motivate more, the discussion that we can have later on. But I'm going to talk some on seasonal forecast as well. So, as always, I start with almost a clean slide. We are here because we provide, we develop, or we use forecasting engine for the wind, solar, from meteorology in general. And the driving condition of this forecasting engine, of this technology, comes from the demand of information we have, obviously. This is the motivation. This demand of information comes with a demand of quality. It's a pen. And this is something that we see in the wind energy market, because it's not the same demand that we have in Germany, in Portugal, that in India, or that we have in Brazil soon, because there is a different technology development, different market rules, etc. And obviously, we need to have a translation between what the forecast provide and what is this demand of quality that is the metric. But many times it's not very clear what is the demand, what is the quality we expect, how we assess this forecast. No? At the end, this is like a loop. We can have a good forecast, but we don't know how to provide this information or how we use it. Or we want a strong demand, and the forecast cannot provide this, as it could happen. So at the end, in anything that is forecasting, there is an issue in the perception of this forecast. So without going to the psychological aspect of the perception, because it's not this, I don't think it's worthless here. But what I'm going to talk is about the perception of doing the forecast for the wind industry. So a few words on who we are. We are Vortex. We are just here in this building. It's not the whole building, it's just one office here. And what we do is we provide wind model data for the wind industry. But basically it's based on a mesoscale model that we run mostly for hindcast, but we also do forecast. Well, our business and technological model is basically on a very automatized system that do the downscaling of all the reanalysis to provide very high resolution data for the past. And this is so we can provide a set of products to fulfill the different demand that you might have in the pre-construction and also in the post-construction. And also we started to be also doing the same, but for the solar. So in terms of forecasting, we provide short-term forecast. That is, for the wind industry, means day ahead and intraday. But we've been involved in more R&D activities with seasonal, a little bit in sub-seasonal as part of the project, and we are very keen and very interested on all this climate. So we also touch aspect of what is the low frequency variability of the wind regime. So in terms of the short term, I think we can agree that this is a typical scheme of what is the methodology employed for power forecast in the wind industry. You have a global or mesoscale model that provides you the meteorological input. You have information from your power production, historical, and and near real time. You have a statistical model that is all these deep learning methods, Bayesian, neural network, support vector machine, etc. Even linear methods, even that you use to find all the hidden patterns in your that correlates the power production and the meteorological information that you have to bias correct all the systematic and non-systematic errors, and then get also the power production. You have to monitor that. You have validation, and also, as has been pointed out today, you need to deliver this, so you need to have an interface. You need to make it very simple for the end user to have the access every morning without needing to go into many details. So what we see that is becoming the forecasting for the wind industry? Well, today it's like a commodity, something that is a very competitive market where you might have many providers that works with hundreds of projects all over the world with different situations, different demand, different end users. So what we see also is that the value of the forecast is going down. So I don't dare to tell you how much cost to provide the forecast for a wind farm, because it's something that if you don't know it, I don't want to tell you how much is the value now in the market. So at the end, for the middleware that we are, Vortex and others that you are here and others that are not here, it's very difficult to justify for the end user and for you to put an effort to decrease the absolute error, because this price is not really paid by the end user, by the market, by the competition. No? So at the end, we are like evolving to a very low cost forecasting system. This is not a complaint. This is like a vision of the real practice of when you. Because here we are not making the forecast for like a big Red Eléctrica in Spain or in Portugal or in Germany. We are talking about companies like the Maya Energy, Maya Eolis, or many of these companies that are all over the world, that they have their portfolio, small, bigger, but they have different demands, and you want to serve this kind of project. So, because at the end, each wind farm project that you want to provide a forecast requires some supervision. You cannot automatize everything, because you need to look to the data, because there is not a standard in terms of the input data you receive from the SCADA, you receive from the end user, you receive from these multiple hands that manipulate the data. So you need to put you need to look to the data. You need to check the quality of the power data, because at the end is the one that is going to make the forecast. So the methodological data is very important, but at the end, if you want to forecast power, you will need observed power to train your statistical model. So that is some things that we see that is a big issue in terms if we are thinking in how we should develop the technology, is that in the real practice, there are these constraints. No? That we can think in very high sophisticated method with the best observed data, but at the end, it's not what we have when you go to the real world. No? It's the same issue when you are doing a mesoscale model with an ideal case, and then you go to the real world. You see that the same conditions are not applied. So. Next slide is just to do them to pass you my comments on what is the seasonal scales in wind industry, and I'm gonna just summarize in 2 slides. That's basically what we are developing now is post-processing methods for the wind industry, because obviously to forecast a longer period, then we really relied on the big institution. It's something that we cannot do it here. Vortex cannot do it on other company. It's something that you really is much more complex in some way, and you need to the idea of ensemble is very, very relevant. We need, at the moment, we need to assess the reliability of the seasonal wind predictions. This is something that is still, we don't know how good are the seasonal predictions at the moment. We can be positive, but we need to provide some data to convince the community. And then we need to do a lot of lobby, because seasonal forecast is not very known. It's not, and this came to the first slide. We don't actually know the demand of the seasonal forecast, so it's difficult to motivate the development of the seasonal forecast technology if there is not a real tension that someone knocks in your door and asks you, we have this demand. Here it seems that it's the other way. We have this forecast technology. What will be your demand? So I think we need to change this. And also, at the end, we need to know if we have to put more effort in the seasonal scales. It's something that is not really a crucial aspect. To answer this question, we are involved in a project called SPECS, one of the last FP7 projects. And it's a big project that tries to develop the new generation of seasonal forecasts based in Europe with European technology. And we do a small package there that are in the pilot application, and one of the pilot applications is the wind industry. So we try to pass information that other developers within the project to the wind industry and to test some cases. And just to finalize, many people ask how can we do seasonal forecasts. Actually, it's because we answer a different question that in short term. Obviously, we don't want to, I think you know, but it's always good to repeat that we don't want to know which will be the wind in the 30th of July of 2016. We want to know whether the next summer will be above or below the average. Then is the question if the wind industry, this information is important or not. If it's sharp enough to be of use. To be interesting, yes, but to be of use is something that still we need to know. And I've been in other projects that try to work with the end users, etc. And my conclusion is still I don't know exactly if there is a sharp demand of seasonal forecast. And I am very motivated in doing that, but if I had to be honest, I don't have all the arguments to see the wind industry is demanding a sharp solution. And we can forecast the future in 3 months because we just want to see the average. And there are some processes in the atmosphere and the ocean that has like a slow memory. So this is where we rescue some kind of predictability that help us to advance information. But it's not always possible. Not all the seasons has this predictability. Not all the regions has this predictability. So this is something that we are working. So last slide, and then I have a small annex. In seasonal forecast, we need to deal with this predictability, to know where we have predictability and where we don't have. Obviously, the model uncertainty is critical. It's something that is part of the game. We have now so many seasonal products developed by a reference center, but we have a huge constraint that the wind is not there. We have temperature, precipitation, sea level pressure, but wind is not there. When the wind is there, we have the zonal and meridional components. When we have these components, we have monthly, so we cannot obtain the wind speed with monthly zonal and meridional. So it's when still we need to get hold of this information. Obviously, you can create your own post-processing that from other variables you calibrate with the reanalysis and get some estimation of the wind, but I don't think this is a solution, an emerging solution now to use this data, but probably we need to ask these providers to make the wind available. Another issue is the perception. I think we still don't know what is the need in the wind industry. And what we have to do now is work in this post-processing of this information, obviously. Well, this is homework in seasonal forecast. no need to go to there. And I'm gonna end it with an appendix that probably, Clive, you will know more about this event. The guy you see there, this is because I saw this week a presentation of a presentation about climate, and Tim Palmer from Oxford University mentioned this example, and I said, okay, I have to bring it here. So it's not my idea, it's from Tim Palmer, a reference in climate sciences, who, to justify the meaning of uncertainty, put the example of one of the worst forecasts ever, at least in the recent history. It was in '87, so almost 30 years now. Time flies. These are the BBC, and the data were provided by the Met Office, I guess. But well, this is not to criticize the Met Office. No, it's not my intention. So it's this guy. There is on YouTube the 5 minutes forecast report of that day. This guy was saying, okay, tomorrow it's going to be a little bit windy. We have some pressure, low pressure coming. But don't worry, it's going to go to the south. Maybe it's going to dissipate before he arrives to Spain. The day after, the huge hurricane that UK, well, it's almost a hurricane. In terms of scale, it wasn't a hurricane. It's not a hurricane because it's in the mid-latitude in Europe, so we don't call these hurricanes. But this hurricane, this low-level pressure was channelized and destroyed, but touched the southwest of England. So it was like in 24 hours we passed through a small windy situation to a hurricane. Obviously, and in '87 they used it as a deterministic forecast, I guess. And in 2011 they rerun the forecast with the technology of 2011. So you cannot see it because I take this from a paper. So it's, but in the top left, you see two boxes. On the left is the analysis, what we really have. And this blue is the low pressure, 90 millibars, so it was massive in a particular region. And in the top right is what has been forecasted with a deterministic forecast. And then in 2011, with the technology of the Met Office in 2011, they rerun the model with an ensemble. And in the ensemble, you see that there are many of the ensembles that came with the same. These two are the two initial conditions that could be. We see that are almost the same, but they are different. And these initial conditions that are very similar at the end ends in these patterns. No? So you will see that some of the results provide this blue dot that is maybe a hurricane, maybe not, and other not. So if you take the ensemble average, you don't see the hurricane. If you took the ensemble and you say there were 30% of probabilities to have this strong winds in UK, it was like the strongest wind in 300 years. So this is something that is like an example, it's historical. It's 30 years ago, probably now it's not going to happen anymore. But it's important to visualize that sometimes even the ensemble means doesn't provide you these streams. No? And I think this was very good for the Met Office because then they could convince the Department of Defense or the minister to buy a biggest computer. No? So there is nothing. So I don't know if I said about many things, but the idea was more to motivate a little bit the discussion that we have now.
No comment from Clive?
Yeah, I mean, at the time it came back to a lot of the forecast was overinterpreted at the time, so they shouldn't have been as confident as they were about predicting where the winds were going to be. That was one of the things that came out of the inquiry afterwards. They actually changed the forecast as meteorologists training as a result of it, how to interpret. But this is a very interesting case because it's such a small scale feature And actually it was sensitive, the deterministic forecast was sensitive to some very localized wind observations which were missed in the operational run. If you put them in, you got almost a much better forecast. But as you can see from the ensembles here, an ensemble mean won't give you, as you say, an ensemble mean won't give you anything.
This in our perspective could be the same situation that we see with the ramps. That is probably one of the hardest things that we have to that affect the forecast is when you have a strong change of winds in 1 hour, 2 hours. You can have an ensemble forecast with different situations of the ramps. No, this is something that it's important.
Yeah. First of all, thanks. This was really a great start for the next session. For the discussions, I appreciate that you also told about the situation in the market. So I will not comment further on it because we discussed this in the next session. But thanks for that. And but I don't agree that this is not happening today. I mean, it's not happening in that extent today. But I think we observe probably once per month something that is maybe not on that scale, but on a similar scale. And this is, I think, what we have to become aware of, that this is where we have to develop tools, because we now have the raw data. We have this kind of stuff that we can see 30% of the ensemble members give this kind of weather situation, and it has an impact on many things. In the power system, it can have a great effect. It can have a devastating effect on many things. But I think this is really where the future lies, and that we can generate products that have this extreme. And this is what I think has not been really understood in the power industry, that having 3 or 4 or 5 deterministic models that are optimized on the day ahead, they do not give you the extremes. They may give you a better average score, but they do not give you these extremes. So they will not tell you that tomorrow there might be so much power that the energy prices go negative. That there is a 30% chance that this is going to happen and you can react on it. They will only give you the average, and this is, I think, what we have to communicate to the market, and also that this requires development, and this requires that the prices for forecasting and the value for forecasting has to be raised again.
But you don't think that if we concentrate in this part, that because I see 2 parts, this is the meteorological, the issue, and then the input data. But in this one, I think the issue is to increase the resolution of our weather models. No, because the solution here is not a question of resolution. It's a question of ensemble, probably initialization, probably other aspects, the data assimilation. So, and I work with Vortex, work with downscaling, and with experience I gain, or people I met and in exchange, I think the resolution is not the main target for forecast for wind power.
Since I have the micro, may I make a comment myself? His speech was half about let's say results and half about perception. And I think that even before than improving the results, a work with the perception should be done, because maybe the wind was very bad here, badly forecast here, but maybe the rain was well. So some farmers were very satisfied that day. So there is a, let's say, basic problem that there is not a universal metric about the weather, and even know about the wind. So we have experienced a very specific problem in India. We are forecasting a whole region of wind farms in India, and they are expected some absolute errors, while we think that it is much fairer that the error should be related to the rated power. But this then both we are frustrated because there is the metric is not a standard.
I would like to follow on that, because there is the forecasting part, and I think the wind energy community is not so much into improving that, because we kind of expect the net offices to bring the best quality data, but we can definitely work on standards, and I don't see a reason why we should not have a data standard for the SCADA, or we could have enough, minimum quality.
A data standard for the SCADA is a massively lack in the industry.
And not only there, but also standards for quantifying errors in terms of wind energy specific interests. So I don't know if an IA task should really be a forum to kind of lobby.
It's actually part of the
task. I can see that. I mean, as a precursor to a standard. But the industry will adopt it if they have a benefit. That's so.
The SCADA standards are actually adopted to a large degree. These IAC 6850.
That's for the communication.
For the communication, yeah.
The common information model. There is one from IAC for weather station and so on, but no one adopts the standard. So it exists, but no one keeps the standard, and that's the problem. I think we don't need more standard. We need people start using the standard.
So pedagogic and work.
Can I ask a question about the seasonal forecasting? What do you see the main use of that, or demand for that, would be from wind power users?
Well, the main demand will be portfolio modeling for developers, owners that have wind farms in different regions, so they can probably make some numbers based on the chances to have both regions above or below the anomaly. It's the thing I see from what we can get now from the seasonal forecast that are maybe the tercile probabilities, so to have average, high, and low. This is what you can distinguish with the seasonal forecast today. You cannot go further. You cannot precise more than that. And then we can say, okay, we can provide more information, but I think that the use is in people who doesn't need a very precise value, just an indicator of how the things are going to go.
What is the problem that they're going to apply it to? What problem do they have to apply it to?
At the moment, is that I think the climatology provides them more confidence than the seasonal forecast.
I'd like to comment on that. I mean, so So it's a very good question. You know, what would it change? I mean, you could ask. I mean, if you had good seasonal forecasts, because obviously we look at the financial results of, you know, in my company and other operators. I mean, it's you do that quarterly, right? So it's sort of almost seasonal, if you like. And typically you'll hear the CEO say something about, you know, the wind business unit has performed, you know, above expectations, but it's due to, you know, winds that are above, you know, what we expect from climatology. Well, he won't say climatology, but you know, that's sort of the message. I mean, and there is sort of a production budget that is based on climatology. I mean, and even if we knew that, you know, what next quarter would bring, I mean, I don't think we would really. What would be the thing we would change? I mean, I can't really, because that budget is put down on a yearly basis. I mean, so I'm not so. I think it's more from people who hydropower. I mean, they're really interested in the seasonal. I mean, I don't see so much use of that. I'm sorry to.
You know, for example, one.
Years there has been incentive where it was actually, we were also thinking about this was something we have to get into, because the providers of green electricity had to stay within a certain band and had to deliver that much green electricity to be to reduce some fees that they don't have to pay if they delivered the green energy. And for that, they needed to have forecasts on a monthly basis for 3-4 months ahead to know. No, but it helps you to be able to plan whether you stay within the limit or not.
Yeah, but if you're drifting out of that band, I mean, what are you going to do about it?
Well, that's another question. But if you know that you're doing it, you can take action. I think that's what it is about. That's what forecasts are about, right?
Maybe maintenance. Maybe so there are some maintenance works that have to be planned some months ago.
I think we can skip my.
Just to add something. Just to add something to what Corina was saying. In fact, we use seasonal forecasts, but probably bad ones, in the Monte Carlo simulation. And for what? To understand in the next 10 years or 20 years if the conventional generation you have in the system is enough or not for the level of wind power that you actually have. So this gives you the reliability of the power system. So this could be a potential use for the seasonal forecasts. We do this as a consultant services for the system operator of Portugal. So if you have a seasonal forecast, you know more or less how much wind power you can expect in the system in the next 10, 20 years, and you know if your generation portfolio you have is enough or not as a reserve capacity and so on. Another one could be also the extreme weather phenomenon in 1 month or 2 for a DSO, to plan the teams to be on the terrain to solve all the problems we'll have with the blackouts and so on.
Well, the issue is that we cannot resolve this with the technology we have here. We in this European project, we have some pilot regions where there is some predictability. For example, northeast of Brazil, where there is also an energy security issue with the rivers. So the coupling between the wind and the hydropower in the northeast of Brazil is very interesting, and there is a signal of predictability. So
Brazil, the problem they have with hydro, when they have the dry years and they have actual blackouts for several times, if you could predict if you'll have a dry year or not, is a very valuable information for them in advance, of course. I don't know if it is easy or not. I'm just in the...
No, yes. And the other region that is in the pilot is northwest of US, that is a more mature market, and also India. So there are things going on, but it is still
I should venture a forecaster coffee break. Well, actually, I now cast a coffee break. And then afterwards, we'll have one presentation from Corinna that was planned for this session that is going to be starting the next one. But that's already starting the discussion very well. So I think we have mixed a little bit from the discussion from the last session into this here. So it's fine. See you again at, what's it for? the excellent discussion that was from the next session. So now we swapped the two. And Corinna is having one more case, if I understand that correctly,
yes,
to show us.
I will try to make it short. I guess most of you know, so I will not talk about ourselves. I will try to go into this, start in a way this or continue this discussion about what is the perception of a forecast. And I've said maybe sometimes it's good to go down to the basics, and this is what we often see a forecast for today. It's cloudy with some sunny spots, and what's happening in reality, it's slashing rain. And everybody asks what has gone wrong with the weather forecast. I guess everybody knows this. And some know this one. This is then when we come to power. We have the blue line, a forecast, and the dotted black line is a measurement, and the forecast just didn't see this peak that is happening, and that can be very expensive if we are a trader. It can be dangerous if we are a system operator, and everybody asks what's gone wrong. And like Gil has already showed, this is a forecast of cloudiness and precipitation. The green is precipitation, and we can see the isobars, the blue lines that show that there is a low pressure system. And we can see, and this is just 9 model runs of precipitation and cloud cover and wind speed, and we can see it looks very different. And this is why something like that happens. It's because it depends which kind of model result you have used to generate this forecast. And this is another one. This is then when we go to wind power, we can see that there are some members that have very strong winds and thereby also wind power. This is just applied a power curve from the wind speeds in 100-meter wind to get a kind of a potential power production. And what we can see is that I'll go back here. We have some kind of uncertainty, and the reason for such a failed forecast is often that even if we have a number of models, if those models are optimized on mean absolute error or root mean square, they actually suppress such peaks. And even if we have a number of them, it doesn't help. We don't get the outliers. So this is one of the things that that has to be understood, that this is a perception thing. So I was thinking about what are the reasons for uncertainty in power generation for renewables, and there are really 2 things that I think are important. This is the weather uncertainty, and then there is also an uncertainty in power production, and this is also sometimes underestimated in larger systems like the German system. We have heard this morning. There are unknown production patterns. There are wind farms that are also in Spain. We have heard the measurements do not reflect the available capacity. So even if I have a measurement of a wind farm and I don't know the availability of the wind, the capacity or the availability of the wind turbines, I may get a completely wrong signal into my system. So there is something called an uncertainty in power production also. So let's have a look again here. What is uncertainty, and when do we get concerned about it? I think we are all clear that we get concerned about if we are a TSO or a system operator, if we reach a level of uncertainty or error where we don't have enough reserves. And that's what we can see in a system like Germany. They are they have started to curtail. There is lots of curtailment happening right now. So this is then what I said. Even if I have a number of forecasts, if they are all optimized to give a good average score, I just don't get that peak. Whether I should trade the electricity or whether I should manage this on the grid, we have this problem that the deterministic tuned forecasts, they suppress extremes. So what can we do about it? And this question has also come up today already, that what we can do about these situations is that we get more information and we get a warning. So here I have taken that case, and this is based on 75 ensemble members. And you can see at the very top there, the measurements are just going out of the maximum. But if we see such a forecast, we can also see that, of course, that red line will not give you a good score in an RMSE if this is the one that you are using as a deterministic forecast. But it's giving you an indication of situations where this type of situation can happen, and this is what we have to learn to deal with and to use when we make our planning. So what causes uncertainty, and are forecast errors really only due to weather forecasts? And this is something that meteorologists always will say yes and no. Of course, we do have errors in the NWP models, but this is not all. So some reasons for the weather uncertainty can be the weather analysis and forecast is never 100% accurate. We have problems, or we have issues in the formulations, that because the formulations in the NWP models, they contain assumptions. They do not hold for 100% of all weather situations. The area that our model contains and can be too small, so a low pressure system can run through within the forecast cycle, and if it's not coming into the boundary, it's not seen or developed in the same way. The model resolution can be insufficient, or it can also be too high. We can also have small-scale phenomena that are not resolved, or that are resolved but result in large errors because they are predicted at a spot where they don't happen and are not there where they happen, or not at the right time, etc. And then one of the things, of course, that cause uncertainty, this is that the atmosphere is just not linear. So some reasons for power and wind power uncertainty can be interpretation of weather forecast can be wrong, and this is one of the issues that I really want to emphasize. It's the perception, it's what we order, what we want. Higher resolution is not always going to solve our problems, the problems that we have or the issues that we want to solve. So the different forecast algorithms for power can be better or worse, also dependent on the climate, the area we are in, the complexity of the area, etc. So you cannot say that one model of conversion is much better than another one, always and everywhere. And whoever is going to claim that is not going to say the truth, I would say. The availability of information from wind turbines is a huge part of the power uncertainty that is absolutely and often underestimated. If we don't know the availability of the capacity that is online, we do generate wrong forecasts, And if this is also coming into the trainings, the power conversion models are made right for the wrong reason and the other way around. So this is something that we really have to understand, that if we do not have good measurement data, we can also make our models wrong and get a result out for the wrong reason, a good result out for the wrong reason, and then in many other situations we get a wrong result out for a reason that that could have been avoided. So there are also technical reasons for different production patterns. I mean, the manufacturers are conditioning the turbines in a way that that reflect their needs, their interpretation of how the turbines should run. Sometimes in very windy conditions, turbines are set up that they actually never reach full load because it saves on maintenance, and that's valid. But if your model gives full load and the turbines, you don't know that the turbines are actually set up that they should not give full load, you're making your models wrong, and this is part of this uncertainty. So you make a physical situation wrong by some kind of wrong measurements or statistics. And then unknown curtailment, we all know that, or shutdown or maintenance that we don't know about is a huge issue. So this is again that extreme situation that I want to ask, when does it become a nightmare? This is, of course, when that error there becomes too large, and this is then a full 75 members for the same case. The previous picture was just an excerpt of that. There we can see that if you see all these, even though you don't see the details, you can see that the difference of the various models is so extreme that we can say one thing for sure: we cannot trust in a single result, and that's something that we have to make into products that we can work with. So at the time we made even more than the 75 forecasts. It was part of a research project where we took this event up, and there is a report about it you can find on our webpage, or just send me an email so I can send it. We actually made 10 experiments where we had at the end 750 forecasts for this event, and what you see here are the mean forecast of the 75 forecasts. So it's always an ensemble mean of different setups of the models and model resolution, model area, etc. We have made a lot of variations to find out what is the cause and can we actually model it. And what we can see, and this is a confirmation of that, a mean forecast of an ensemble is not enough. It's like a deterministic. We didn't get any of the experiments. We had a mean forecast that hit that measurement, which is here, that pink line. So this was one of these cases where we can say, when we look at the individual forecasts, we have these outliers, as I showed here. The red line is the maximum forecast that actually got that peak, but we of course also have the green line, the minimum that didn't get it, and the means and so on. So it is a very complex situation, and this is where we can say there are many situations, and we see it in our daily forecasting, probably once per month or every second month, a similar case, and all we can do is learn to interpret outliers. When do we have to act upon that we see so many outliers that tell us here is some kind of danger that we should act upon? Yes, the results, we have seen this. So I will not go into detail here. Often I can see that if the meteorologists or we as modelers try to explain to our customers or end users what has caused this, there are things coming up like this was a cold, weak, low-pressure system located in the Norwegian mountains, mid-tropospheric advection from the mountains, and so on and so on. And there was convection on small scale that evolved and interacted with this in the middle of the troposphere. And the end users then are there and saying, is this now something I have to understand and learn and can use at other cases also? And this is what is the problem about explaining why a forecast has gone wrong, because the clear answer is no. It's a complex area, and if we try to explain why something happened in a certain way in a language that others don't understand, it's practically impossible to justify why or to explain why, and that we cannot really do something here and now, that this type of thing cannot happen again. And so I want to throw this also into our discussion later, that we have to become aware of, on both sides of the table, that explaining why something has gone wrong is equally difficult than understanding and drawing any conclusions. This is another case, and this is in a way to bring this into when is something critical. This is when we get to errors that are so huge that they can bring a company like Statkraft to bankruptcy. That's not so easy, but what I want to say with this is that there are, of course, critical amounts of critical megawatt amounts of error that can really generate damage on a financial and on a grid security level. And this is what we have to become aware of with increasing penetration, that with increasing penetration there is really a threshold where we have to learn to deal with uncertainty and see what can we do if we see something like that our errors can actually become critical. This again just the same on a horizontal plot with wind power. We can see, if we look upon the North Sea there, between Denmark and Germany, where we now have in Germany a lot of large offshore wind farms, we can see the difference in the min and the max, upper and lower, and the mean of 75 forecast, that there are also gradients, and if those gradients are very close to where different wind farms are standing, then we can actually have full load or almost no load on the wind farms. And if we have 5,000 or 6,000 megawatts standing from a meteorological point of view, what we can see a very small area, this can cause these critical errors. And we see this, and it's an issue. And that's why I also think that we really have to take this serious. And this is also because one of the things that we have to realize is that even if we go from forecast to forecast and we have uncertainties, the uncertainty, of course, decreases the shorter we come to the real delivery of. But we have also varying quality, and we have variable biases of our forecast. So with new updates of the meteorological models or updates of measurements that we make on the shorter term, we sometimes would create an overproduction and an underproduction. So this is something that that we need to take into consideration when we do trading, for example, or when we look on reserves in the market, that the forecast error decreases over the forecast horizon, but it's also variable. So day ahead trading alone on the long run, this is the message of this, is insufficient. So we have to really go the UK way of rolling markets and so on, where we really have the possibility to balance. So what can we learn from these examples? I think what we really can learn is that we can never hope to rely that we receive a perfect forecast. This doesn't exist. And there is something that is called short-term forecasting, which is in power the next few hours. This is going to be more and more essential. The more wind power and solar power and variable power we have in our grids, and the forecast errors therefore have to be balanced along the way, and dependent on the forecast uncertainty, the market development. So that's the liquidity. We have been also talking about this from Effie's presentation, and also congestion constraints. So the amount of data and information from ensemble forecast or uncertainty forecast may be complex, but I think there are tools to help condense this to important information. And now I'm not sure how much time we should spend further. I have a few tools. Okay. 2
minutes on the questionnaire.
Okay. So I had prepared some tools, but I'll stop here. So if there is a question coming up or in the discussion later on, we can take that, and I can show some of the tools that that can be used. Now I just need to get this other presentation. Yes. Oh, that was the one here. F5. One of the tasks in our IAA Wind Task 36 or work package tasks was to look on the state-of-the-art use of uncertainties in the power industry, and I want to quickly tell what we have been doing in this as a flyover to the reason why we are actually here. And the reason why I want to tell you about it is that I really want to encourage everybody that is here that has not yet filled out our questionnaire or interview questions to please go to our Dropbox and take one, or contact me and I'll send one, because we really want to get an overview of these gaps and misunderstandings of how we can use uncertainties. And what we have been planning so far is that we want to have a kind of a work in progress project here, and so we have 3 phases, but once we have gone from the first to the second and the third, we will go back and start not from scratch, but we will use this information and see, have we forgotten something? Should we take more information of certain things in? So it's going to be a dynamic process, but we want to have as much information from the industry as we can, and one of the 2 objectives that we have identified is that we want to focus on information and not on person or organization. So I know that many of the traders and the system operators, or they usually are not so critical, but the service organizations and power producers, they are afraid of giving information, and that's why we said we want to make this anonymous, so everybody can decide whether they want to tell who they are or not, but we are not going to use any name or organization name. If we get it or not, that doesn't matter. If the team knows it, it will never be used in any analysis more than that we categorize the different areas: system operators, traders, service organizations, power producers. So there will be not more than that category involved. So we designed a questionnaire and a submission procedure to be confidential. So the interview documents, they are on this Dropbox, and we have made some language packs. At the moment it's Danish and German, and that's only because we had people that helped us doing this. So we will also get some French and Portuguese and Italian, and I have got some people that volunteered to help with this. And everybody that can do it in English is more than welcome to do this, so we don't have to translate it again, but we want to also make it easy for everybody to participate. And so what we have done in the questionnaire is we want to have a kind of a general character questions and more forecasting and uncertainty questions to get this broad overview. And so we have 18 questions, and if you are fast, you can do it in about 15 to 20 minutes. If you take more time, you can also use an hour. But so we wanted to keep it to a level that people can also use it. And so what we have done now already is we have set up the questionnaire, and we have done a first evaluation, so we can now make an action plan. And this is the first results. We have got 24 questionnaires back, and we can see there is mostly system operators that have answered, and some 3 traders and power producers. So we have already quite a good mix, and also in the country mix, where there is unknown, the 6 unknown is where we don't know where they come from, so they were really anonymous. Some we got back and could identify this was from that country and that country, but it's not so relevant. For us, it's only relevant that we do not get bias in the answer. So if we get 50 answers from the UK and no answers from the from France, there will be a UK bias, and that's what we want to avoid. So that's why I wanted to present this and showed you that there is at the moment a bias on Denmark, and this is because we have put in extra efforts to get some people to answer the questions, and that also shows that we have to be careful. And that's why I want to advertise for, please help us distribute this and get as many of those questionnaires back, so we don't get any country biases. So the very last thing to tell you, some first preliminary results that I found very interesting also for the discussion now is that we can see that 61% of the answers indicate that uncertainty forecasts are still somehow associated with speculation, and there is this fear of that speculative behavior leads to loss, or also just to use it. And we want to work on this, so we can see this is a kind of a problem. We have also seen that 98% of all that have answered are using multiple forecast providers or forecasts, but less than 10% make use of uncertainty forecasts. So it's this what I wanted to tell. There is a difference in using multiple forecasts that are that are tuned with deterministic models, and you're using uncertainty forecasts. So we are now kind of aware of this. We have some data that really show us that we have to do something about it. And then we can see that less than 10% of all organizations employ meteorologists or engineers with a kind of an atmospheric science education, or and I think this is also something that have to be brought up, that to build up knowledge in many of the energy businesses. I think we do have to have people educated, or at least with a kind of a background that help bring this understanding of how weather models, how weather works into the operation. So that's it. Thank you.
Thank you very much, Corinna. I think we'll leave questions to the discussion section, because now it's up to me and maybe George to come up with some introduction to the discussions that we wanted to have. And we've, since not all can be here, we've actually asked the people who can't be here to come forward with what they think are the main issues. And one of the starting points was an answer from David Lanahan from UK National Grid, who provided a good list of stuff. But there were several that came. And of course, it's not taking place into a total vacuum. We've tried to answer that question of research gaps and what should be the next steps a few times before. So there's quite some experience in how to structure that. But still, the answers that we see now and that are coming from industry are partly new. Essentially, what we wrote in the strategic research agenda for the European Commission in 2015, where George was the head of the integration working group and I was the secretary of that, was that we should look into new and improved measurement techniques and get all that data into the models, try to get integrated forecasting models that can sort of get all scales correct, try to be specific for the specific use cases, and of course the old-time winner, improving probabilistic wind power forecasts. And well, that was more in the methodological part, and then we had improved probabilistic tools for essentially the same thing, and improved for probabilistic forecasts of everything. So combined forecasts of generation, demand, and price. Because as we've seen in a previous presentation, that actually can have impact on each other. And then during the EWEA technology workshop last year in Leuven, Lars Landberg put together a good session on crowdsourcing the future, where you could Twitter in or well, have some issue list and vote for some issues. And the ranking of the issues was, again, probabilistic forecasting, without being more specific than that kind of headline, was getting the biggest impact. And some meant, okay, we should be getting better at making those probabilistic forecasts, and some meant we should be better at using those probabilistic forecasts. But data availability was actually one of the points that we've had discussed throughout this work packages, throughout this day as well. And data availability is a big issue that we are also having a bit of a task here in the IEA task. NWP development is ongoing and will be ongoing for a while. until we have the perfect model, and even then we need to figure out what that perfect model can do and why the weather is wrong in comparison to the perfect model. And then we had users' needs short-term forecast, which I think was meant very, very short-term, so hour ahead forecasts and real-time, or in other words, nowcasts, and so on. And then there's a whole lot of stuff that didn't really get much attention. So what? Thanks for Corinna for actually putting together a lot of this presentation here again. But I didn't want to want her to stand here and have a third presentation again. So what does it actually mean if the NDWP model does not develop certain phenomena, and the meteorologist think well, the phenomenon was not resolved in the model, or we got some phase errors, and the power engineer's view is essentially, oh, that's all crap. Which somehow is both only part of the truth. So the connected issues that we had from the external views, from the people behind the screen, were nowcasts, especially for difficult situations, where we have small-scale weather, where we have weather that, in the UK example from 1980, when was it? Weather that rapidly develops in a way that is hard to foresee. Thunderstorms, small lows, and so on. Then we've also heard already before that sub 1 hour temporal resolution would be nice. We've had some trials with actually writing out the results of the weather model every 10 minutes, but it's difficult to see how much that actually improves the overall usability of the forecast, because there's only so much information to go around in the model. There's meteorology also below 1 kilometer spatial resolution, which is a bit related to what we've heard before, and the example where that came from was that sometimes we have quite localized weather phenomena, especially offshore. The example used in that case was the Thames estuary, where you have specialized offshore phenomena, and Dan has done some work on particularly this. They actually need some high-resolution modeling to capture that, which in many cases might be just increasing the complexity of the overall problem without yielding much more quality in the results. There were stability issues mentioned, especially if you have a daily pattern and the stability is considerably wrong. Low-level jets, farm-farm interaction. Farm-farm interaction, of course, can be calculated, but it's not part of the numerical weather prediction, and it's often not part of the wind power forecast very directly, because the wind power forecast is for one farm in most cases, or for a region. So in some way this is taken into account implicitly in the direction dependence of the power curve, but that means that you want to have a good direction forecast. Do we have that? Do we have good measures for the quality of a direction forecast? Then also what we had during the day were short-term ensembles. What we know is that ECMWF and other big organizations have an optimal spread after 2 days. 2 days is a bit too much if you want to trade day ahead, and it's definitely too much for anything that happens intraday. Rapid update models have been mentioned. The quality of the extreme quantiles in the probabilistic forecasts is a quite specific problem, but obviously how do you tune the the extreme quantiles of the probabilistic models if you have a really small database to work with? Do DSOs need different forecasts than TSOs, or is that just the same on a different scale? Then one question that came up was, are there penalties for bad performance of forecasts? Or, as we put it the other way around in the talk of Gil, how do we actually manage incentives for improved performance of forecasts? Is winning a benchmark process a bit on chance, or is that really showing that you are better than the competition? And but is the money that comes out of it enough to actually keep improving? So what, in a way, it's connected to the overall business case within the wind power ecosystem. And then the last thing from Gil was seasonal forecasting. What's the business case for that? So that's some of the issues that I had, and this list is by no means exhaustive, because I'm pretty sure that there are more things to be considered. But that's what we want to come up with, and we've put in some issues here just to reiterate what happens. The double penalty that we've talked about a few times. Here's an example of that. If you have a high-resolution model that does the shape of the temporal development nicely, but at the wrong time, then you actually get the first time before and the second time during the event a higher penalty than if you'd have just a average production forecast. That, of course, is bad for your overall error scores, but it might actually be the better forecast because it's more usable, because you see that there's something going on, and even if the timing is wrong, the people that use it might think it's a better forecast. And if you have the sub-hour or sub-kilometer phenomena, that's related to the discretization in the numerical model. So sometimes you get new effects that haven't existed before, and sometimes it's just increasing the numerical workload. I mean, how much better is a 1.1 kilometer forecast to a 3 kilometer forecast offshore?
Yeah, but we can also see on that figure there how the vertical and horizontal resolution changes what the model actually sees.
Yeah. And then obviously there's farm-farm interaction, but how relevant is that really? It's important that you get a better direction signal, and one of the examples here is from ERA DTOC. That's some satellite pictures from SAR images, synthetic aperture radar, which looks at the capillary waves on top of the ocean, and from that signal can actually determine the wind speeds on a map. Oh, well, on a snapshot given from that satellite. So what you see here is here is, for example, London Array and the wake behind London Array, which or here in one of the Belgian offshore wind farms, which actually does stretch quite a long way. So how do you account for those effects? But in the direction, if you look at Greater Gabbard and that influence on Thanet, you have to be pretty sure about the direction forecast to actually show this. And even though here below we show that we can actually calculate those in the magnitude without the proper direction forecast, we don't really get anywhere. But how important is that really? There's a bit of research to be done. It's a similar thing for cutout, though probably more urgent to know, because cutout is actually affecting quite some bits of the power system. But what does happen if more farms get storm control and stay on for a bit longer and just keep producing. Is that still an issue then? Same essentially also would go for icing. You put up turbines in the far north where you get icing and where you can't produce for some time in the year. But once you put in anti-icing systems, a lot of the problem is actually taken care of by those. Is the own production of that really an issue? Cutout in high winds. Area between full load and cutoff can be quite small, so it can be quite sensitive to actual modeling results or to which ensemble member you choose, respectively, what exactly the weather is deciding to do. And of course, the uncertainty gets quite high in those cutoff cases, which again can be predicted. The uncertainty that it's close to 25 meters per second can actually be used operatively. Then, of course, there's the whole issue of probabilistic forecasts. What's the decision-making process behind probabilistic forecasts? How do you employ them in your business models? How do you employ them in your working life as an end user? That's where I think, according to the official time schedule, we have 10 minutes for discussion, but I'd be happy to extend that a little. So here, I got that list of collected issues, and while I talked, there was that icing issue that I didn't really have on the list before, which on my account can go to... go to here. But as I mentioned, all those slides are going to be on the website afterwards for not only looking at them yourselves, but also for sharing among colleagues.
Just to help to start the discussion. Just for this list, one aspect that is not really mentioned is round forecasting. I think it's part of the extremes, which is quite important. Probabilistic was the first in the other list of the crowdsourcing, but I think this is a point that it's interesting to discuss, because in my opinion, the probabilistic forecasts are I mean, you can evaluate them with respect to some criteria like reliability, sharpness, etc. And what we see today is that we have forecasts that are quite good on this criteria. So if you improve maybe the error of in terms of deterministic is not good, but if you improve that, you improve it also for deterministic forecasts. So I have the feeling that probabilistic forecasting is a bit put very high in the rank. However, the use of probabilistic forecasts is really an issue that should not be underestimated. So the main question I would like to address is, okay, here we have a list that is the result of brainstorming, crowdsourcing. It gives some shopping lists of things that would be nice to do, interesting to do, etc. The question is, why we need to discuss them? Because do we need to prioritize them, to put some priorities? Because today, for example, if these issues, I have a fundamental question. Today, if I see the value, the price that the end users put on the table to buy forecasts, very low. So it seems that they don't. It seems that probably it has become a commodity, and they are quite happy with that. And I wonder first how much money they would be ready to put on the table to solve any of these issues. Would that be, would they put any money actually? Or should we try to solve them through other ways, like, for example, the development of collaborative projects, like European projects? We had them in the past. We have done lobbying to the European Commission to finance new projects, like after the last one was SafeWind, actually, which ended in 2012. But although we have mentioned forecasting in research agenda, etc., it never came through as a topic in the calls of the FP7 or the last calls or Horizon 2020. So this means that there is a general feeling that research in forecasting is somehow, that forecasting is a mature field, that not much research is needed, or at least not a priority. We can see it on the way that these priorities that we fix are received, and also from the industry. I mean, it seems that at the end of the day, maybe the forecasts that are provided today by the service are sufficient, and so the price is low. So
yeah, let me use that I have the micro. I was in Leuven in that rotation in the chart. It was in the chart, and I think that ranking of the probabilistic was biased because of the audience were modelers. Okay. So they were this was their interest in selling this, but okay, this is only an opinion.
No, we often mix, and we have to be careful when we make this kind of list, what we need, what is good to have, and where research is needed. And I think we should try to find the areas where some more fundamental research is needed, to go back to the basics, so that we produce new breakthroughs that can really improve the performance of forecasting.
I would like to pick this up with respect to the incentives, because I think the question you raise of the value of a forecast has to do with what do I get out of it, and a forecast never should cost more than what you can save as costs or increase your income. And we can see as a provider that there are more and more of the system operators that are, let's call it in our perspective, the high-end customers. They have come up now with incentive schemes, and the incentive schemes are there really to make sure that the forecaster can use some resources to improve, and improve means that we have some resources. If we want to get the incentive money, to put it plain, we have to use some resources to work on where we see there are problems, there are issues, there are things that we see in the operations that we can improve. And in most cases, at least it's our experience, it really helps both. It helps us to develop, further develop, and it also helps the customer, because they can be sure that there are resources used because the forecaster wants to get the incentive payment. In the market systems where the traders, like Statkraft, for example, I have been a number of times bold and said, well, why don't we make an incentive scheme so we get, instead of getting paid for the forecast, we actually want to have a percentage of your reduced balancing costs or your income. And I have not found that trader that wanted to do this. And I have done this in a situation where I said, well, somehow I'm desperate to find out what is really the reason, why is there, why is the value of the forecasting is gone so much down. And maybe I would like to give this question further to Effie. She can maybe comment on it. If I would come today to you and say, make you that offer, how would you react?
So, okay. I think the answer would be no, not because of me. I have to be honest. But at least from our perspective, I can only speak for my company and what we do. And I think that we help the companies, at least the companies we work with, to evolve. So we give them the chance and, of course, the money to do research. We also, if they agree, we also pay them according to their performance. So when there is value, we try to support it, at least from a company perspective. And it is money coming from the trading teams. So clearly from the trading teams. It's not from the researching teams from our company in Norway. The trading teams in Germany, they want the best forecast possible. And we do this. We try to give more money to the companies so they do their own research. And we also pay them according to their performance. So some money will be theirs, of course, because they have to cover their expenses. And if they deliver something better, they will get more money. But would it be accepted by a company to be paid based on the performance? So if we get a forecast that it is extremely bad, would you or would a company accept not to get paid? So I can also return the question. I mean,
yes, that's absolutely valid, and I would say yes and no.
Yes.
If I think, and we have also experienced this. This is not a question that is new. So I mean, everybody has costs to do some service, and so I would not agree to a contract that gives me nothing if I'm under a certain level. But I would certainly go very low on the cost to say, yes, if we can reach a certain level, we start to get paid. But so I would say this would probably be something that many forecasters today wish that or would like to see, that this is actually happening more, because you can't develop and you can't improve and you can't work if you don't get paid for what you do. And Gil has also demonstrated this very nicely, that especially on power producers, for example, also, they want to have a really good forecast, but they don't want to pay for it. So if we all know that our most expensive resources are human resources. So if I can automate a process, then I can offer it cheap once I have developed it. But so I want to see the return of this development, but then I can also offer it cheap. But the moment I have to have a person involved in verifying certain things, then there is a cost to that, and we all know that. And that's where I think where the gap has started, that this is no longer valued, that it's like the forecasters, as if we are robots. Maybe we can employ some robots at some stage, but I think that's far away.
Okay, so this is a different topic, but just to answer the question from George, I think I have a little bit bias because I gave two two topics there for that slide. One of them was with the DSO. So I think this is where I think we can do something innovative. In DSO, something innovative. Because it's different. You need to predict much more time series than you regularly do here. You need to predict more variables like the reactive power. You have a mix of renewable generation and load, so it's a completely different problem in my opinion. And there is funding for that, private funding. For example, we have at INESC a private project with DSO to do that. They don't have any forecast. What I think is that probably the business model is not having a company supplying the service, is having a company supplying the software. And the software is at the end user premises. So in that case, it's not selling a service, you sell a maintenance of a service. So this is where I think we could have in the future projects with innovative contributions on this. For example, one of them is the way you need to model with the DSO spatial temporal uncertainty, either with an ensemble, either with the statistical trajectories and so on. And then you need to include that in their tools, optimization tools. And that's not easy at all. So we have made a small project with Pierre Pinson about that. And the conclusion is that you can include all this uncertain information, but then it takes 24 hours to give a decision. So you see there is a lot to improve there, is one thing. The other one with the extreme quantiles, I think is also a critical point for system operators because they operate with a very, very small risk, so the quantiles and the extreme events are quite critical. And even for traders, we see today that there was some extreme weather events where if the probabilities are completely wrong, even if they use uncertainty, they take bad decisions based on that. Even on that, the level of research is very low. So I think these 2 points, in my opinion, are important points.
DSO, we are doing some work on that. Maybe we can talk about that in the break. But in terms of ensembles, there are some questions which I don't know the answer for. Maybe some here do. What should be the ensemble size? And it's not clear to me at all. And if possible, I would like to see this as a task. And what should be the ensemble quality? There was mentioned in Corinne 75 ensembles doing 750 ensembles job, and how should be the perturbations for wind power applications. I don't know the answer to these questions. Maybe some people here do.
I think the answer is nobody knows what the perfect size of an ensemble should be. I think we have made in various research projects experiments with up to 900 ensemble members, and in some cases they managed to simulate a certain case, but this is then not something that can be used operational. I think every med center and every forecaster that is working with this is deciding on the size according to the budget. And that is actually, I think that's the best I can come up with. And you decide on a kind of a strategy, and then you have to somehow follow that strategy, because it's a very complicated and complex and expensive process to generate real-time ensemble data. And so I think there are different systems that are running, and the longest is the ESMWF EPS from 1993, I think they started, and there has been probably made many changes, but the the general system in itself has not changed, and that has also a value in itself. And I think that there has been a lot of work in the research being done to try to analyze what is the right strategy and how do we evaluate ensemble data, but that has been mostly on statistics. I think what we have to do, and maybe this is also something that we will probably work here, is to find standards to evaluate what is really for power for an end user. It doesn't tell an end user in a trading company if the reliability is that much or that much. This is very technical, so we have to also find some standards to evaluate whether certain types of ensemble data or ensemble are useful for certain tasks. So I think this is what we can do, and I think that's also what we want to do here, to make a kind of a categorization so that the end users can more understand which type of ensemble system is useful for which type of application.
I also want to make a comment on sample size. I don't know what's the perfect one, but it depends on what you want to do with it also. So for example, one point I can really directly say is, for example, this in data assimilation, when you want to assimilate, to get information on your errors, and not just on the errors at one place, but on the error covariances, then actually you need higher moments, so you should need more ensembles, a bigger ensemble size than actually for the forecast, as long as you just want to forecast, let's say, mean variance, something like this. So it's, there is no, you cannot say I need so many ensemble members, or also you cannot say just more better. I mean, they have, ideally, all should have the same quality. So you have to increase it and still represent different weathers. I mean, so just changing a little bit doesn't mean that it really, you get additional information. With a Cosmo ensemble, Cosmo D ensemble, then we have combined perturbations of little different, you are from the physics parameterization with small differences, then with different boundary conditions, different models using boundary conditions. And the other problem is, as I said, calibration is important. You can still see also the boundary model, so not all the members are actually equal. They are slightly different. Or I mean, it's good they are different, but there is also systematic differences. So the point I want to make is it's difficult to increase the size. So it's still that you get really more information in it, and as that then also the size depends on what you want to get out of the ensemble.
Thank you. So in some sense, I think this is a very good test case in trying to find the maximum ensembles, at least for a benchmark case, and see what would be the reasonable amount. Because if you need to run 1,000 ensembles for that case, and you are running only 100, and if you know that you are not going to get it, then there's no point of using ensembles for that case. And so at least we can have a criteria saying for this kind of problem, you don't need to have an ensemble situation, because it's not going to capture it. But yeah, also, of course, the perturbations are important, how the ensembles are created in space also, but that's another problem by itself. Also the boundary conditions, if it's going to go to mesoscale. So I think there's a lot of things that can be done solidly there as a task.
I'll just to apport more information about the size of ensembles first, okay? From the point of view, if you're interested from ensemble, what is more what has the high probability to happen, okay? That is from the practical point of view, okay? It's in some sense you are interested more in the mean, on the average. Probably with from the practical point of view, with 10, 12 members, it's enough, okay? If you are more interested, what Corinne shows that it's some extreme weather events or some outliers, you need for sure more than 20 members, okay? Okay, probably ideally you have to have 40 or 50 or something like that, okay? And the second thing in the ensemble, if you are very interested in winds, what you have to perturb, especially when you have a weak synoptic forcings, okay? You have to deal with the interaction with soil and oceans, with the atmosphere. You have to perturb that in some way. Another thing is you have to perturb what is doing one of the parametrizations that deal with winds, the planetary boundary layer, okay? Some way, for example, it's using different planetary boundary layers, okay? So this increase how you take into account the uncertainty with winds.
Yeah, let me just comment on, I don't remember which presentation I saw, two events with let's say the same spread of the ensemble, and one, the reality was just in the middle, and the other, it was just at the extreme. In a demonstration that the uncertainty and the accuracy, they may not go together. So you could have a very uncertain episode, and then you just match the average. So you don't have any clue for the next error. So this is maybe a more fundamental question than going into the details of the size of this ensemble.
So I don't know if you want to keep talking about ensembles, but I think in the context of the use of the ensemble in wind power forecasting, the one thing that we have to be aware is that we calibrate the ensemble with our statistical model, so this automatically will reduce the ensemble spread. So it's very artificial, because at the end, especially after 2 days, the ensemble will be closer than what was originally forecasted. So it's something that I think is something that sometimes we don't take into account.
So if I really have a problem seeing like 10 and 12 ensembles being good enough for any distribution. And of course, I think it's just a way of making things easier for us, just to take 10, 12 ensembles. The models are big. Also, the question is it in state or is it parameter space? If it's in parameter space, maybe smaller ensembles are better. And also, how do we say 12 ensembles are good? I mean, did we check it with 100 ensembles? Did we check it with 200 ensembles? And what is the criteria? Are we checking the RMS, or are we checking, what are we checking? The background error covariance, or if you are, there was mention of improving the model with observations, are we checking the observation covariance matrix? So these are all things which are not clear to me. Thank you.
Sorry, I'm not sure if you understand quite well what you're asking to me, okay? But you're asking what we are doing to improve the ensembles, what we are looking for. What you are trying to say, where you say you are comparing to one?
No, there's a 12 ensembles we have taken, and we increased it to 50 ensembles. Did you compare that?
No, it depends what is information you want from your ensemble. Probably if you are interested in something close to the surface like winds, you need a 25 members ensemble, something like that, at least.
Let me try to stop the ensemble issue with just a comment for Elfie. I remember that she said that in her company they had quantiles, that is just a result of the ensemble, and they didn't know what to do with this, because somebody has to take a decision. And if you have an ensemble, you don't have it is not easy for you to take a decision. You have a problem. So somebody should go further than this. Don't you think so?
I have the feeling that there is an academic flavor in the discussion, because the final product that is used is the quantiles, and the quantiles are different than the ensembles. Okay, so I mean, what we have made tests to produce probabilistic forecasts. This means to produce the PDF for each time step using different type of inputs, ensembles, the mean of ensembles, the mean and the spread of the ensembles, different ensembles made of Francis, MWF, etc. And the model that gave the best quantiles at the end, BTF, that is the product that's used, was a model that was using as input the average of the ensembles and the spread. So the number of the ensemble does not count, because anyway you cannot use it because you have issues of parsimony and all this. Well, this was a test. It depends on the ensembles, it depends on the test case. Probably if we go to details, we can have different cases. But I think the end users are using quantiles and PDFs, etc., this kind of probabilistic information. Scenarios is a different type of information that can be used in case you have a deterministic model to take decisions, and you don't have a model that can take as input directly probabilistic information, like quantiles. But then it's a different issue, because I see Ricardo.
It depends on the problem. If it is a unit commitment, the ensemble probably gives you the temporal correlation of the errors, which is something that you need for that problem. But just to answer about that, there is the multivariate energy score, which is one of the metrics you can use to evaluate the quality of the ensemble set. So you can evaluate with 15 members, 50, 100, and then you get an idea of how much are you improve the representation of that uncertainty. This could be a method. I don't know why use 50 or less or more, but this is one possibility. There is other metrics. Okay, just.
Yes.
It then quantiles is generated from ensembles. Quantile quality is going to be generated based on the ensemble quality. The distribution is going to be based on the ensembles. So they are all linked.
I think we have to defer the proper size of the ensemble in a sampling outside on the terrace afterwards in a smaller group. Are there any of these other issues that ring a bell? Are Jens and I the only guys here who are interested in icing? Well, ice in a nicely colored drink, maybe with a small.
No, but what do you want to know about it? What is the question?
Just to get away from.
I have one, not about icing, because in Portugal it's not a problem. It's about the data simulation. In Corina's slide, she mentioned that atmosphere is a nonlinear process. So I'm not aware of what models are used for the data simulation, but I know that in signal processing they have, for example, nonlinear Kalman filters. So it's just a question. Is it possible to have some kind of a non-linear data simulation in the current models, weather models, or not? Okay, because so use a non-linear Kalman filter.
We have our Kalman filter, and I mean you have the 40 bar, so it's also non-linear. So I would say, yeah, usually when data simulations is non-linear. I mean, often the question is also about there are assumptions often that, for example, errors are Gaussian distributed, so which actually they are not. So there are a lot of assumptions which the reality is more complicated. So it's not perfect at all, but it's not definitely not just linear. So.
Now, one question might be.
I have a comment to the icing. What we have found, especially in Scandinavia, in Sweden, icing is a huge issue, and if you need to know whether there is icing or not, it's really quite complicated. But what we found is that it's really only the outliers that we see in our ensemble, that can actually provide that information, how high the risk is of icing. And there you come into this problem, of course, of the false alarms. And that is an issue that has to be worked with. But again, this is also how much is provided to develop further algorithms.
Yes, so on the icing, I mean, what we have found from benchmarking forecasts for iced sites is that if you've been the situation based on whether there's icing or not, you basically find that there's some dedicated forecasts. They work very well when there's icing, but they actually make the situation worse in all the other cases. So what we need is some sort of two-step process where we do what we call a categorical forecast. So basically, likelihood of ice or not, and then we decide what to do based on that. Just as a very brief comment.
In terms of data assimilation, the question, there are many methods to do non-linear, non-Gaussian data assimilation. The problem is the computational time, not the method, the practicality of the method.
Well, the other problem might be that some of the data that we're looking at hasn't really been used in data assimilation so far and needs some research to actually improve the models. The yet other question is what data, as also Corinna mentioned in the beginning, what data would actually significantly bring the quality of the models forward? Where do we not have data so far that would actually bring the models forward? Because we have, at least in Europe, quite some data from the surface, but and we got some satellite observations of the surface, which makes things near the surface relatively well observed. But what about higher altitudes? Is there anything that we can do to get there? There's this cost action that someone mentioned on the ceilometers. Does that actually have gotten any tangible results yet?
As I said, the problem is to keep the data in the system such that it's also kept that it's kept by the model, so that you don't have just a forecast which is better. Its analysis is better, and then the forecast is maybe 1 or 2 hours improved, but naturally you want to improve it for several hours. Or naturally, I mean, if it's nowcasting, then that's what you want, 1 or 2 hours. But to get it into the weather model in a way that you really it's kept for 12 hours, 24 hours. That's more difficult, and yeah, that's. I don't know if somebody can say, "Oh, this will be the solution for this." I mean, we already use a lot of data, so it's difficult to say that adding one or more source of data will make really a significant. You can demonstrate this is a significant improvement.
Come back to Helmut's presentation. He shows where you had flow-dependent errors. If you think about ramp situations and positions of lows, which we've seen examples of, we can give you real problems. And it's likely that improvements in the treatment of the errors and the assimilation, in the data assimilation, is likely to improve forecasts of those situations. That's where you're going to get more improvements than any one extra observation type. I would think that it's actually improving methods for how you analyze and get that data in. Because those cases, I mean, the 1987 case is very interesting because it's very sensitive to just what observations you use and where you use them. And again, I suspect, I don't know whether anyone's done a flow-dependent test on that yet, but that was a few years old, the results that Hill showed, that was 2011. If they'll redo that case again with flow-dependent errors and other better methods of data simulation. And I've no doubt that case will show even more sensitivity and better forecasts. If you want very short-term forecasts, you'll get a better forecast eventually by improving the methods rather than a set of observations.
Just to that, also a comment. I think that was a really good point because it has been shown in many of the extreme cases. Also, I remember the 99 storm over France and Germany, where there has been also done, I think all European med centers have done enormously many experiments, and it's whether certain observations are rejected in the data assimilation that can actually either generate this extreme low or not, because if we have extremes, this is where the data assimilation most likely actually rejects such measurements until it's more confirmed in, and that's why it often then the forecasts fail. And that's again the point where we have.
Tune just on that.
Yes.
You get that forecast
Yes.
the whole series of extreme.
But it also means that all observations that come into the data assimilation have to have a certain standard, because otherwise the data assimilation is just rejecting it. And that is why if we think about getting power measurements or measurements from wind turbines into such systems, there has to be a very different quality. Otherwise, they may come in, but they are immediately rejected. And because I think there are many places around the world where there are not many other measurements, so it would be beneficial, but it's certainly, it has to become, it has to get a very, very different quality.
Another question I would like to ask. Is anybody aware if the meteorological community has their own research agenda for the years to come, for the research and development? I mean, this is something that is, this kind of research agendas with priorities for the future, we develop it in different communities, different sectors. Does the meteorological the community of the meteorologists has a research agenda for the future? I mean, it could be for us, I think it would be useful to know. I would be interested to know if they project that, I don't know, in 10 years, maybe they will do developments to have 1 hour updates, or I don't know, to increase that or that. I mean, I think some of the things here are priorities that are from that concern that community, and I wonder, does this community fix them as priority for themselves?
as I said in the summary, then at DWD, project now for the next years is the what's called the seamless prediction, or the seamless prediction is the big theme, I would say, of all weather service. So trying to make integrate, going from nowcasting to the short range to the medium range as smoothly as possible. So, and then also naturally rapid update cycles is that's something which probably will be done in a few years, but you have to show that really there you need. Is it worthwhile to make a new forecast? To make the new forecast, you need new data which to assimilate, but still, is it enough new data that you really can show an improvement? So that's definitely planned. I would say, assume many weather services do it, but.
I'm not interested on the research agenda of DWD or Meteo France or other. I'm speaking about the community. Like, for example, in the wind sector, for the wind industry, we have the research agenda that is made by the technological platform for the wind industry. For the PV is the same, for smart grids the same. So this gives somehow the hints to the European Commission, etc., for where they should put the money for research and development. So of course each company has its own priorities, etc. But my question is precise: as a community, do you have this kind of agenda?
I don't think there's an overall community strategy in that sense, but most major centres are following very, very similar lines of development. So for global models, they're probably going down to 10 kilometres in the future. The rapid update cycles, we're about to introduce one next year, probably with a new computer, but it'll be a very much an experimental test, early version of that to see how well it performs. Other places around the world are doing similar things, so there are very, very similar things being done in most places. The meteorology below 1 kilometre is probably that's more of a contentious development. Not many places are probably going to go below 1 kilometre. Use of probabilistic forecasts and short-range ensembles. Nearly everybody in Europe is doing that in some form. They're doing it elsewhere around the world, and so there's all common themes. But there's no one saying you must concentrate on this aspect. It's just shared problems that we're trying to address. And use of data, use of satellite data. There's a lot of cooperation between weather centres looking at new data forms to see how well they perform. So some centres will concentrate on one particular aspect of an observation type, and then others will adopt it in their system. So there's not in the same way as I think you're asking, but we share the same problems. So. But there's different approaches within that. There's different approaches.
I don't know if I'm right, but is the simplest issue here, isn't it to have 1 hour temporal resolution or half-hourly temporal resolution? Because this kind of data inside the models, it exists, no? That's just that they are not saved. I don't mean that that's going to improve the forecast a lot, but we do need alpha-hourly time step for forecasting. So isn't there here an issue which would be the easiest to answer? And another comment on probabilistic forecasting. I don't want to have another debate on it, but on rain forecasting, we start working on clustering. So instead of having 50 ensembles, we have 3, 4, 5, and that's really interesting because you don't get quantiles, but you get 3-4 trajectories with associated uncertainties, probability, and that's another way of maybe using probabilistic forecasting. And I haven't read a lot about it on this field.
Depends what you want to do with the sub-hourly data, really, doesn't it? Are you just talking about the immediate nowcasting and the first day? I mean, after that, the phase errors, the timing errors will get so large, I can't see that that's going to give you anything extra. So really, you're only asking for short range, extra temporal resolution. Yeah, maybe. I mean, one of the problems with Met services is just the sheer volume of data, and the other thing with massively parallel codes, which you have to use for timeliness, that the more I/O that you put in, that slows the model down dramatically. So you have to kind of balance it off. So that's probably why a lot of centres don't offer sub-hourly, if they even offer us hourly data.
We have in a research project for 4 years ago in the HR Ensemble project actually made the experiment and wrote out native data from the model in the native time resolution of the model, and that can be done, but I think the problem is that you want to have maybe 100 points, but the volume is increasing by a factor of, I mean, you get, instead of 1 terabyte data, you get 10 that you have to handle when you do the modeling, and I think this is the real issue. And that's why the med centers are also not very cooperative. Because the amount of costs that are generated are not paid by the end users, because you don't want to pay 10 times the price for your 100 points, but the med center or those that do the modeling have that extra cost, because if you do the write out in that way, you have to do it for everything, and I think this is the issue.
Well, one thing that can be said on the advantage of writing out a bit more often is that Martin did a PhD where he wrote out sub 10-minute results, aggregated sub 10-minute results to a variability signal in there, and that actually pointed that this one correlated nicely with the produced error for, what was it, up to next day forecasts. So there is some value in showing into looking into some of it, but sometimes it might be enough to look into statistics within the hour, which you then write out just once, because as you say, the I/O is the thing that takes a lot of time, not the calculating an extra number.
So, sorry, Matteo Vitale from Convex. Just to reconnect to his question and a question about having output in, for example, 10-minute resolution. In Convex, we tried to use 10-minute resolution models, and we saw no significant improvements with respect to 1-hour resolution models. But the biggest problem was the data handling, because we created 300 gigabytes of data per day. So it was a big issue to handle such data.
Okay, one proposal I would like to make that would be useful for the IEA task. We could maybe try to make an inventory of, ask the participants what are the ongoing activities of research and development on this or other issues in the frame of collaborative projects or PhDs. It would be nice to have a list so that we, for example, next workshops, we can invite people that can present some innovative results. And it would be good, I think, to be aware of what is ongoing now, I mean, in terms of development and research and development.
Okay, so it's time for more research, it seems.
The ice symbol.
Yeah, maybe we should take that question up tomorrow again, because we did it actually quite well. We managed to get this good discussion ongoing for 45 minutes past what our initial target was. And I think that's now the moment to conclude this workshop, which I think has worked out quite nicely. I mean, we got a large list of issues. We got some issues added to it. We actually, even from that list of issues, we got some illuminated in the talks before that didn't even know that they were issues beforehand, but didn't know that I had them on the list before we... It's a magic trick that is made easy by a PowerPoint where you can add stuff along the way. And anyway, I hope you all enjoyed it. I'm sure I did. And yeah, tomorrow, for the ones who will stay for tomorrow for the IEA task meeting, we'll meet at 9 again to discuss more of those issues here. And we'll have a bit in the morning on project mechanics and going through the work packages, and are continuing this discussion then in the afternoon until probably successively people are going off to get planes. And having said that, I say the good old Danish tak for mad, because Pep has graciously sponsored the coffee breaks and the excellent lunch today. And finally, I'd like to thank the speakers from today, which had excellent presentations. And there must be some plan for now, isn't it? I'm sure they serve beers out there on that little terrace there. Do they?
They play live music in this terrace, but only on Fridays.
Dang.
So.
It's called Little Friday in Denmark. Is that good enough?
Yeah. But for those who are not staying nearby, this is not the center at all. Okay, so it is not a very. It's not. There's no very fancy places to go around. So. But the metro will bring you in 20 minutes to the real center or even to the beach, which is very nice at this time of the year. We really didn't prepare anything, but as I said in the morning, just feel free to ask and for advice, so we could even arrange something. Since the touristic offer is so great. If there are not very big groups, this can be handled, okay?
Thanks. Yeah, thanks for coming.
Thanks for coming.
See you tomorrow. Most of you.
Okay.